All right, so we've arrived, 9 charging systems. So you guys know that's the alternator. There's a little bit more to it than that. So kind of in a similar theme, you guys know newer vehicles, a lot more electronics. More computers, power windows, power mirrors, power seats, power everything, electronic power steering rather than hydraulic power steering, right? Just a transmission, for example, now is electronically controlled, where it used to be hydraulically controlled. More electronics means charging systems with higher current capacities than their predecessor. So back in the day, the alternator didn't have as hard of a job. Now, if you think about it, when you start the car, the battery's not really powering everything. The alternator is basically putting out all the current to keep the battery charged and to run all these things. So the charging systems are under much more demand. So generally, we're going to focus on an alternator. Sometimes the service manager, the service manual will call it a generator, and we're going to make sure you understand the difference between the two, although it's not critical. So it needs to be able to supply all the increased currents, which requires more mechanical energy from the engine. So this is a bit of a misnomer. Like if you have a power steering pump on your car and it's running the steering, it's robbing your horsepower, right? So if there you are in your 2000 Honda Civic, you know, like what people will do to make those a little faster is they'll start pulling stuff off, eliminate the power steering, eliminate the air conditioning, right? Weight reduction, but also it's not, if it's being driven by the belt, it means it's putting extra load on the crankshaft, means it's consuming horsepower. That's true. But the thing is, when you get rid of your hydraulic power steering and you go to electric power steering, you're thinking you're freeing up horsepower, and in a way you are. But remember, if your electric power steering draws on the electrical system, that alternator has to supply it power. The more power that alternator has to generate, the stronger the magnetic field is going to be in this alternator, right? So the stronger the magnetic field is going to be, you know what that means for how hard it is to turn it? Harder and harder and harder to turn it, okay? So just keep in mind, with all these accessories, it's going to make the alternator work harder, and that is going to actually put a little bit of a load on the engine. To finish what I was saying about power steering though, power steering is mostly needed like when you're in the parking lot trying to park at Costco when it's crowded and you're turning and you're looking, right? With a hydraulic power steering, you know, the power steering pump style, you're running that pump all the time. So when you get on the freeway, you're still running that pump. That's pretty inefficient. So the reason we've gone to something like electronic power steering is when you're in Costco, we can send a whole bunch of power to that power steering system. But then when you're on the freeway, you don't need the power. It's much easier electronically to say, don't send any more power. We don't need it, right? So we are getting a fuel savings and an energy savings by doing more and more electronics. It's just when we do need it, you'll need the alternator to work super hard. Okay? And then just keep in mind, the charging system is much more complex now. Just like what I just said, there's a lot more demands on it than there used to be. So back in the day, the alternator would basically recharge the battery after you started it and run a minimal number of lights and like a little bit of things like an electronic ignition, you know, and that's about it. Make sense? Whereas now if you jump into, let's say, a brand new, I don't know, something that's got a lot of, say a lot of features. Like let's say it's a Ram TRX. You jump in, it's got a big old center screen. It's got heated seats. It's got ventilated seats. It's running GPS, navigation. It's got all these lights and LEDs and features and a big LCD screen instrument panel. And it's got all this type of stuff. And at any point, you might have a lot of your electrical accessories running, or you might have just the minimal number running. Make sense? So the alternator needs to be able to keep up with it, but not overcharge it, be able to charge it in the most demand with the electronic power steering, but also if you're just going straight on the freeway with your lights off, with all your heated seats and stuff off, we don't want to overcharge the battery. So it's actually gotten much more complex. But the main goal, as always, is going to be trying to meet output and economy requirements. So if we consider emissions and fuel economy, if you have your alternator overworking, aren't you putting a demand on your engine? Which means you're burning more gas, right? And you're having more emissions. So we needed to be able to keep up, but not necessarily overwork. So we've really gone to computer control. It's much more efficient for the computer to control the alternator so that it's not overcharging, but it's also able to meet the minimums. Cool. So that's kind of the trend you'll see. Now, what's the alternator's function? Or just the charging system in general? When the engine's running, and generally when the speed's above idle, the alternator should supply electrical power for the vehicle and recharge the battery. Now let me make this like a little bit more of a basic overview. If the engine's off, what is powering your little computers and your clock and your radio memory presets? First, if it's off, the battery's given just a little bit of electricity. So if you leave that car sitting for, let's say, a month, that battery may be dead. Makes sense? Remember we talked about the parasitic drain, right? All systems have a parasitic drain. So your battery powers it while it's not running. Now what should happen when you go to start it, ready? Put the key in, turn it, or the push button or whatever. You should energize the starter motor, and the starter should just give a small amount, just a big amount of power, but for a very few seconds. Make sense? And boom, the engine's running. At that point, the battery just took a big chunk of its energy and it lost a bunch to turn the engine. Make sense? So your voltage was, let's say, it was 12.6 when you shut it off. As it sat for a few nights, it probably went down a little, 12.5, 12.4. Let's say it settled at 12.3. Then when you went to crank it, that battery spent a whole bunch of energy turning the starter, right? So by the time you're actually done cranking it, it's probably down around like 12, maybe 12.0, just in the course of a few seconds. Cool? At that point, when the engine runs, the crankshaft is turning, it turns a belt. The belt turns the alternator, right? Once this starts spinning, assuming it's working correctly, all of a sudden, you should get a big spike. So this should put out more like 13.5 or 13.8 or 13.2. It's a little hard to say because a lot of times the computer controls it, or the voltage regulator on an older style will control it. So we don't have a very specific number. But let's say you were to start the car and you were to put your meter on the battery and you were to measure 12.3, 12.2, 12.1, 12. 11.9. This isn't working. Make sense? So the most down and dirty way to understand this is the alternator does nothing at all until you start the car. And then when you start the car, the voltage should go up and up and up and up. Not 12.6, but like 13 point something. Probably not even 12.8, 13 point something. Make sense? So if just the most basic, if, like, we were talking about maybe a person in the parking lot had a dead battery. If they have a dead battery, that could be a charging system problem. But it could also be a battery. Remember how the plates get sulfated? Cool, yes. And then there's always still the possibility that maybe their battery's actually good, but they have a problem with their starter and they think it's a dead battery because they turn the key and it just goes click, click, and they're like, I think my battery's dead. Maybe the thing that I would do is just kind of, let's just say I had my meter, okay? I could do the diagnosis very effectively. I put my meter on the battery. If the battery is 10.1, that battery's it's discharged. Yeah, it's a dead battery, exactly. So it either A, needs a new battery, or B, needs the battery charged. But see, my meter doesn't test the cells and the plates in the battery, remember? So I'd have to say, well, to start, let's jump it. Bang, I jump it. When I jump it, the power from the good battery should go into the dead battery and I should be able to start it, right? And if I jump it and I go to start it and it still goes click, click, maybe I recheck with my meter and now it's 12.3. 12.3 is more than enough to turn a starter. If it's not turning, even with a battery charged, doesn't matter about this. Now we're looking at a starting problem. Then I'm like, well, let me troubleshoot the starter. Just like last week. You guys remember that HHR, right? Click, click, and then smoke. And then we tried to tap on it, right? So there's some little tricks. By the way, we don't generally want to tap on those, but if you're in the parking lot and you're in a jam, you're going to break some rules, and that's the way it is. But in the shop, generally that's not a real good fix. Okay, so let's say it goes click, click, click. We're chasing the starter. Now let's change it, right? Back it up. You go up to the battery and it's 10 volts. The battery's kind of dead. You go to jump it. Boom, you put your jumper on there. Now the battery voltage comes up. You start it. Vroom. Is the starter good? Yeah, because it just started. Now what should happen to that battery voltage once it's running? Up and up and up and up, right? So let's just say if I had my meter and I put my meter on it and it was still reading like 12.3 with the engine running, what's wrong? Somehow this charging system's not charging. Make sense? So your battery's main job is to start the car. Once the car is running, if your battery voltage remains low, it's all about this right here. Somehow, for some reason, this spinning, it's spinning now, right? Because the engine's running, correct? This spinning should be putting out a bunch of amps on this wire, which should raise your battery voltage. Okay? So if I put my meter on it and it's not reading 13 point something, I'm like, oh, okay, you got, there's a problem with the charging system. Is it the alternator? Maybe. Could it be one of the wires going to the alternator? Yes. Could it be the fuse that takes this big power right here and protects that wire from catching on fire? Yes. So when we say alternator, I want you to understand, I probably mean the whole charging system. I don't know for sure if it's the alternator or the wire or the fuse or the whatever, or it could even be the PCM, the control module, because it controls this. But I know it's a charging system problem. Makes sense? So I no longer really care about the battery that much. I don't really care about the starter. I'm like locked in right here. I'm dealing with this. And we can go on from there. Does that kind of make sense? All right, now let's say you have no tools and you're just in the parking lot. This is, a little bit more like the backyard way, if you will, the backyard, the Mickey Mouse. If the battery's dead and you jump it and you go to start it, and it starts, and you pull the jumper cables off and it dies right then and there, it's a charging system problem. Does that make sense why? This isn't putting anything out, and your battery, see, if you jumped it, your battery was kind of dead, so you started it off of your jump pack or your other car. Then when you removed the power of that second battery, if it dies right then and there, it's not necessarily anything with the battery, although it could still have a battery issue. The main thing is, even with a junk battery, your battery can be totally hammered, just sulfated and plates and dead and worn out and low on electrolyte and whatever. If you jump it and it starts it and then you pull the cables off and it dies, that's a charging system problem every time. Make sense? Even with a junky battery, that car should run and run and run just on the raw output of the alternator. Make sense? So that's the other way that I would do the test. Now, if you wanted to do it super janky, super duper janky, what some people would do is they would put like a good battery in there, hook it up, start it, and then while it's running, disconnect the negative battery terminal. And if the alternator and the charging system's good, it'll keep running. Okay, make sense? Because you don't even technically need the battery if the alternator's working once it's running. Does that make sense? That's not professional. I'm just letting you know. There's an issue with that. Let's say computers. Why do they recommend you plug your computer into a surge protector?
Just in case of lightning.
Lightning and big voltage fluctuations and stuff. Computers don't like big voltage fluctuations. Is that fair assessment? Hard to argue with that. So instead, you're going to listen to somebody in AutoZone parking lot who says, yeah, when you start it, go ahead and disconnect the battery terminal, and all 48 of the computers in that modern vehicle, or 80, are all like, hey, we were running at like 13.5 and now bang, we're down to 12.6. That's not nice. That wasn't considerate. Now, has it burned computers in the past? I don't know. I don't really do it that way. So I'm not saying that doesn't work. I am admitting you could have the car running and you could disconnect the negative terminal and do a diagnosis on the charging system. I'm just saying I wouldn't recommend that. The service manual doesn't recommend that. That's like pretty harsh on all those computers. Make sense? So it'd be better actually to proceed with testing in this like with a meter. But in the parking lot, I get it. You're going to break some rules. Okay? Good idea as to kind of what this does. During this time, it supplies all the power for the vehicle and it also recharges the battery. So now here's point number 2. If this is no good, and let's say it fails that test, like you disconnect the jump pack and the charging is still 12.5, 12.6, You know this isn't working, right? But doesn't that mean it's not recharging the battery? And do batteries like to be sitting there dead all the time? No. So a bad charging system can cause repeat battery failures. Our lead acid battery wants to be charged 12.6. It's happy at 12.9. It's happy at 13.5. Cool. It's not happy at 11.7 and stuff like that. So if you have alternator and charging system issues and it's constantly undercharging your battery, it'll lead to premature failure. Okay? That's why they'll say, you know, if you could take it to the extreme, oh, if it's got a bad alternator, you need to change the battery too. Well, I would say like maybe, you know what I would do if you ask me? I would do a battery test. My battery tester will tell you if the battery needs to be changed or not, you know what I'm saying? But if you don't have a battery tester and you're just guessing, you know, yes, this can cause that to fail prematurely. Cool, and that's kind of what this is showing. If we go ahead and let's just say you get in the car and you turn the key on, did you ever notice the battery light's on, this charge indicator? I had a customer call this the Lego light. Yeah, my Lego light's on. Like your Lego light, oh, I guess it is kind of like a Lego light. If you just turn the key on, 2 clicks, this battery light will be on. Do you know what that means? Basically, this is what it means. Your battery voltage is not above, let's say, like 13 volts. If you turn the key on, but the engine's off, it shouldn't be above 13 volts. How could it possibly be above 13 volts, right? So that would be normal. When you start it, what should happen to this light?
Turn off.
It should turn off, and the reason why, this should start putting out 13 point something. When 13 point something comes out here, it increases the whole system voltage, right? Because this goes right to the battery. And this is connected to the battery. That's why it's a battery light, but like, if this light's on while driving, it's not because of a bad battery. But what are they gonna put right there? They're gonna try to draw an alternator?
So if you're driving and at times that turns on, it's the alternator?
I wouldn't go as far as say that, but you're close. If this is coming on and off and on and off, that means your battery voltage is, when it's below, let's say 13. We'll make the threshold 13 because I have to make a number up. It might depend on the manufacturer. So if this is on the Escalade, I don't know the number. But if you were to put your meter on the battery, if it's below 13, that light will come on. My main suspect is this, but as you get more into these slides, you're going to realize a charging system failure is most commonly the alternator itself. But it could also be the wires going to the alternator. It could also be this connection. What if we had excessive voltage drop right here? That cable goes through a fuse. A lot of times that cable has to go through a fuse box, you know, so overall, if that light's coming on, it's absolutely a charging system problem for sure. I just don't know if I'd go and just slam an alternator on there blind. Makes sense, I do more diagnosis. But you guys, that's a pretty good example. You guys can picture this now, right? You should start the car and that light should turn off. So if we were talking about that car in the parking lot where the customer said, hey, I have a bad alternator, they might, but it's really common, even for people who've started this class, to be like, oh, it doesn't start, starter. Oh, the battery's dead, alternator. Well, maybe yes, but maybe no. So the basic test, if it has something like this, the battery's dead, jump it, start it, go inside and look, is that light on? Yes, uh-oh. Even with no tools, if this light's on and it's running, you know you got a charging system problem. We've got to do a little bit more diagnosis though. But this is something I get pretty commonly, you know, calls and I think in the past couple months, I've had, you know, I'm working with a lot of these, you know, in the ranchos, you got a lot of the ranch workers and their English is pretty minimal. So I get these text messages. To them, I'm Pablo, by the way. So if I get a text saying Pablo, I'm like, okay, who needs what? What you need, man? Where'd you get my number from? Next thing you know, they got my number. And they'll be like, I need an alternator. My question to them is like, how did you diagnose that? Because generally, a lot of the common knowledge with blue-collar people is, if this light's on, you need an alternator. And that could be true. And that probably is true most of the time. But if this light's on, it doesn't guarantee it's this, it guarantees it's something with your charging system. Make sense? So a lot of times we'll try to tell them like, you should really diagnose that. Because the last one I got a message on was like a 2011 Mercedes GL 350 or something. And the alternator was like $400 and the labor was pretty high. And I was kind of like, if you ask me, if you, the car owner, tell me that it needs an alternator, I'm fine with showing up like this. Like, I don't know. I take out some bolts, I put some bolts in, I plug it in, and if it's not fixed, not my problem. Make sense? See, I don't really like to get into those situations, so I'd more say, we really need to diagnose this to verify if it's the alternator or if it could be, something related to the alternator. Kind of makes sense? And I've seen some weird stuff. Cool. So overall, there's your system. Now you guys know this is really a charge indicator.
Was it the alternator one?
When I told him the price that I would need to go diagnose to work on a Mercedes that was stranded in a field, he was kind of like, no, never mind. So I don't know.
Let me think about it.
And that's the thing, like, don't get me wrong, I want to help everybody, but if you're going to really do this work professionally, it comes with a higher standard, but it also comes with higher pay, right? So for sometimes it kind of depends on what I have going on. So the one before that was a dude with a Kia Forte, and he, same thing, hey, Alternator, same type of thing. And I was sort of like, all right, it's a Kia Forte, like it's right on top. And I said, seguro? And he said, yeah, for sure. Okay. So I didn't, if I got to go and look at it, I'm going to charge to diagnose it. But with this guy, he's like, yep, for sure. I didn't even go there. I went straight to O'Reilly's, got the alternator, showed up, did no testing at all, told him, hey, I'm not sure. You're sure. You need me to put it in? No problem. I won't charge you diagnosis, but if it doesn't fix it, you understand what that means, right? Not my problem. Don't know, don't care. But for this guy, the car was dead. He couldn't move. He going down to O'Reilly's without a car is difficult, right? So I kind of understand where he was at, but I did put that one in, it did fix it. But that was kind of like that was a lucky, that one was lucky. If you're going to do this professionally, you understand if this light's on and you're like, bam, alternator, and it doesn't fix it, you, as a professional, that's not a good situation to be in. Make sense? So it's better that we do at least some of our basic checks, basic diagnosis, and say, yes, it's an alternator. I'm going to charge you to diagnose it, but the cost of charging you to diagnose it is a whole heck of a lot cheaper than just slamming one of these on here and having it be wrong and having it not be fixed, and then also having to charge to diagnose it, right? So kind of depends on what your position is. If it's your own car, you do whatever the heck you want. If it's a friend's car and you have a clear agreement that I'll replace whatever you say, but don't try to haul me off into court, say that I ripped you off, then you can do whatever you want. But if it's an actual customer and you're a professional shop or you're working for a professional shop, I would never do that. I would absolutely diagnose this. At least 99% diagnose. So there's some basic simple checks you can do to ensure you don't misdiagnose it. And then there's you can get into really detailed for sure diagnosis. All right, but here's kind of the theory. The alternator produces electricity by what we call relative movement of a magnetic field through a winding of conductors. Okay, a lot of technical here. You're going to notice it's similar to what we talked about with starting. The magnetic field, rotating magnetic parts. Okay, the magnetic field is created by the rotor, which rotates within the stationary stator windings to generate electricity. This is just the parts, okay? So the rotor, for example, is this. It spins. Guess what? You know what the rotor does? It rotates. And you know what the stator does? It stays. That's kind of like the trick, right? To knowing. So this is the long version. The charging system is going to provide electrical energy for all the components. The main parts of the charging system include the battery, alternator, voltage regulator, new term, we'll talk about it, and a charge warning light, and of course all the related wiring. So if you have a problem with the wiring, that could be the cause. If you replace an alternator and the problem was the wiring, it didn't fix it. And remember, these guys call me and they're working out in the field in the ranchos and they got mice and stuff. So I'm always like, hey, if a mouse chewed a wire and I put a new alternator in, it doesn't fix it, we should probably at least look at this wiring, at least look at it. We should actually probably measure it for the correct voltages, right? So I can check all the wires with my meter. And that's part of what I bill for. Cool. But it could also be a voltage regulator or the alternator. The good news for us on the new stuff, the voltage regulator is inside. So as long as it's basically I'm saying, as long as the wiring is good and this is getting the correct signal from the ECM, so I would add to this on the new stuff. If it's the alternator or the voltage regulator, we don't really care because they both come in there. However, because this is class, we'll go to the next level and kind of discuss the two, how you would diagnose the two. On older vehicles, the voltage regulator could be separate. So you'd have to know, am I replacing the alternator, maybe a generator in that case, or the voltage regulator over here? Which one? For us is both. It's kind of like the starter. Remember the starter and the starter solenoid? Could be the solenoid or it could be the starter, but a new stuff, they're combined, so who cares? Make sense? Then remember the battery has to store that electrical charge in chemical form. That's a review. Acts as an electrical dampening device. Oh, what? Okay, you guys know about buffering? You go to watch a video and it's buffering, it ends up choppy, right? It's kind of choppy. That's what's happened with the internet right now. Okay, so if that was electrical, the purpose of the battery is to smooth everything out. So if your alternator charges a little too high or a little too low, you would see that in the lights. The lights would get bright and the lights would get dim. And if it did it fast enough, the lights would kind of flicker. I don't know if you've ever seen a car where the lights flicker a little bit. Maybe not the headlights, all the lights. If the headlights are flickering, that could be something related to just the headlights. But if every light on the car, the headlights, the tail lights, the side marker lights, the instrument panel lights, if all your lights are kind of flickering, I might suspect we don't have good electrical dampening. And the electrical dampening is done by the battery. So here's how it does it. If the alternator is putting out, let's say, 13.5 volts, the battery is taking what it can, but then let's just say all of a sudden you get into Costco parking lot and you turn the steering wheel and your electronic power steering draws a lot, it might actually, the alternator might not be able to keep up. The alternator might drop down to let's say 12.6. Well, the battery is going to buffer that right there. If you had no battery, your lights would be bright at 13.5 and they'd be dim at 12.6 and they'd be bright at 13.5 and they'd be dim at 12.6, and your battery is going to help smooth all that out. That kind of makes sense? So while it's running, yes, the battery voltage will be potentially 13.5. Now when you shut it down, you'll notice it goes from 13.6, 13.5, 43, and it'll settle at about 12.6, but while it's running, it can be higher, okay? So it's going to smooth that out. Now I'll give you a really cool example of how I can use this to my advantage, because all this theory is designed to help you diagnose and repair the car. All right, so if I went out on the parking lot and I went to go get a car that was dead, and let's just say I jump it, cool, the battery's dead, I jump it, I'm going to bring it into the shop. While I'm bringing it in, I'm paying a lot of attention. And if I get in the car and while it's running, I notice the dome lights are they're kind of flickering a little, they're bright, they're dim, they're bright, they're dim. Let's say I leave it running for 10 minutes and they're still kind of flickering. I'm like 99% sure that battery's no good. How come? How come? Who thinks you understand? It's not dampening that well. Makes sense? When you have a good battery, remember the battery's like a puddle and it has a lot of depth. If the battery's good and it has a lot of depth, it can take the extra, it can give out when it's short, it can take the extra, it can give it out when it's short, and the lights will be like really steady, like very consistent. Where if that battery's pretty much totally shot, it'll actually flicker. So I saw this one, it was flickering, and I was like, you know what? Those are flickering a bit. I don't think the battery's good. Let it run for 10 minutes, shut it off, and when I shut it off, try to go to restart, and it was totally dead. Make sense? Because the battery wasn't taking and giving electricity because the battery had no more surface area left in the plates. Cool? So it's a pretty good way to check it. You could have also verified that with a meter as well. And so remember, it provides all the electrical energy while it's running, but not while it's not running. The battery stores it when it's off. All right, so here's some more of the principles, and then this next screen I think is, it'll be interesting, but I'm gonna give you guys a video to consider watching on your own time. Okay, so it's gonna take mechanical energy and making it electrical energy. What the heck's that mean? What's the mechanical energy of this device? Exactly. So the engine's turning because the compression, power stroke, intake compression, power exhaust, right? Spinning, we hook a belt up to that crankshaft. The belt makes this go spinning. This mechanical energy can be converted into electrical energy out this due to how the alternator is designed, okay? So that's what it means by taking mechanical into electrical. By the way, what's a starter do?
Start the car.
All right. It does electrical into mechanical. So see how they're like kind of opposite. You take a starter and the starter's sitting there. If you send it a lot of power, the starter will spin and turn the engine over. So it's kind of interesting. The starter takes electrical into mechanical, and the alternator takes mechanical and makes it into electrical. So they're almost like, it's almost like the evil twin of the starter. Opposite, but similar. Okay, so, and it uses the principle of electromagnetic induction. So that's going to be really simple, really similar to the motor, except again, kind of opposite. Okay, and then a simplified version of alternator. Let's say there was a bar magnet and it rotated an iron yoke. That would actually concentrate the magnetic field. If we wound a coil of wire around the stem of the yoke and turn the magnet, the voltage would be induced into the coil, producing a current flow. Let me just show you. Here you go. So right here, we have a magnet, right? South, north, and it's spinning. What makes it spin, though? In the alternator. In a motor, the electrical makes the spinning, but in an alternator, the mechanical makes the spinning. So the belt is hooked to a pulley, which is on a shaft, and the shaft is spinning this magnet in the simplified form, okay? So the magnet is being spun by the engine, make sense? As this is being spun, you can see it's going to interact with a couple of different coils of wire, and when this is forced through the magnetic field, there's this thing called induction. And so let's say there's no electrons in this circuit. When this magnet spins up here and it interferes with the magnetic field, it'll actually induce electricity into it. That means there will be electricity in here now. And once we do that, and let's say like in this example, this is actually the negative side. So this one coming in here will produce a negative and it'll cause the current flow to go this way. Actually, yeah, that's right. And then this one's coming around and the south is going to interact with the north and produce also current, which is also going to flow this way. Those two passing through the magnetic fields will induce an electrical flow and it'll actually make it flow through here. Now we were talking about the left-hand rule and the right-hand rule last week, which I actually had a video pulled up and I was going to use, and I'll think about it. But with a motor, we're going to use the left-hand rule, and we can figure out which way the magnetic field interference is going to make the current flow. And I thought about coming back to that and going in a little bit more detail, but for engineers, yes, and that's why I really like Tim's input. That's what Tim's whole experience is, electrical engineer. So to the electrical engineer, they really want to look at this and be like, where are the poles of the electromagnets? Where are the poles of the permanent magnet? And then they can determine which way the current's going to flow. But it's good to know in theory, but for technicians, I would probably spend your brain power on something slightly different. So just bear with me on the simple aspect of, while this is turning clockwise, it's going to make the current flow this way. And you'll notice it's south-north, right? Now look what happened when it got to north, south, left to right. These being next to each other, it'll no longer induce a lot of current right here. It induces the most current when it's at a 90. So it's less current, maximum current, less, and when it's actually left to right like this, it'll be 0. Okay, but this is where it gets tricky with an alternator. If it continues to spin, right, and now you can see where we continue to spin, it's actually going to start generating again. It's going to start inducing again, and you'll notice something changed. See, this is south-north, and it's south-north again, but if you notice, we've switched north-south to south-north. So we're actually going to switch these electromagnets' polarity. Does that make sense? And that's going to actually make current flow the opposite direction. And then again, as it continues to spin, it's going to cause no current flow. So if you were to summarize this right here, this is going to spin, and as it does, it's going to induce a current flow this way, and as it keeps spinning, it's going to induce a current flow the other way. It's kind of like they're taking turns. What's another word for when they take turns? If you were stuck in the freeway, or if you were stuck on a road and one lane went and then the other lane went, there's a term for that. Taking turns or alternating. Okay, this is alternating current right here. It alternates. It goes this way, then it goes this way. So wait, doesn't that mean that this is AC if it's alternating current? And there you go. That's the problem of an alternator. If we were to just spin this alternator and those magnetic fields are kind of being switched back and forth, right? And they could do it a number of different ways, even through like commutation like we talked about last week. If we spin this, it generates AC. What the heck good is AC for your car? We don't need alternating current. You know what we need? We need DC, exactly, direct current. So this is how an alternator actually works. Spinning magnet that's driven by the belt, and then electromagnets on the side. And if you have the current flow this way, that'll make a north-south, and if you switch it this way, that'll make a south-north, and it's just alternating back and forth. That's what it does. Okay, kind of makes sense just on the principles. Now, I got a cool video. I'm actually probably not going to show it in class, but if I link it, this is so hard to explain without showing moving parts and animations. But I found a video that's really good that'll definitely help you understand this. And here's kind of the reason I wouldn't make this a top priority is basically like, if you know inside of this piece of junk, alternator, if this spins, the magnetic fields should generate AC. Make sense? That's it. And now if there's something wrong with, let's say, one of these coils, it's not going to generate the right amount of AC, right? The AC current. Well, that's where we'll get a little bit further. Because this is alternating current, we could actually measure how much alternating current's coming out of this alternator itself. But the problem is the alternator itself, you can't really access that. That's all deep inside. So we're not going to take this all apart and be like, oh, how much AC is being produced by the alternating effect. What we're actually going to do is send this AC into a voltage regulator and rectifier, which is going to make it DC. And yes, we can see how much the DC is coming out of the regulator rectifier. Absolutely. They'll bench test it. Exactly. Yeah. Right. So we're going a little deep on what's actually happening, when in reality, it's unlikely that you'll ever be that far into an alternator in a modern vehicle. All right, so this is the word version of that. As the magnet rotates, the positions of the poles reverse, the polarity of the voltage reverses as well, and that changes the current flow, right? So this way, and then this way. Cool? So that's going to generate AC. The vehicle computers, the battery, all that type of stuff, they all need DC. So this is helpful, but not real usable. So we got to take that AC, because it is power, right? Power is volts and amps. It generates volts and amps. So it's power, but it's not the type of power that we need. So what we need to do, a series of 6 diodes called the rectifier assembly convert the AC voltage into DC voltage before leaving the alternator. So by the time you can touch it, right? You can test out here. By the time you can touch it, it's already DC. Make sense? If you wanted to disassemble all this stuff, you could actually go deep in here and you could measure the AC, but why? We don't really do that because the voltage regulator is internal on that. Part of the reason I like to go into this though is, let's say, is anybody interested in working on something other than a car? So I can tell you all about how the car is, and that's going to be 90% of my focus, but let's say you're interested in working on something else. How about a motorcycle? Motorcycles, that diode bridge, it's remote. So they actually don't have an alternator per se. They have like they'll call it a stator, and the stator will actually generate AC, and it'll come out of the stator as AC, and then it'll go to a remote mounted regulator and rectifier. So if you had to troubleshoot like a motorcycle charging system, this AC is actually kind of important to know because there's going to be 3 wires coming out of it, and each one of them should have a certain amount of AC. So let's say each one of those wires should be producing 20 volts AC. You just literally put your meter on AC and see, are you making 20 volts? Yes. Are you making 20 volts? Yes. Are you making 20 volts? No. Uh-oh. What's up with that one? Make sense? Then you could troubleshoot the stator. But let's say they were all making 20 volts and it goes into the regulator rectifier, but then the regulator rectifier is not putting out 12 volts or 13.5 volts of DC. You'd say, well, the regulator rectifier is getting the AC from the magnet spinning. That part's good. But when it goes into the regulator rectifier, it's not converting it from AC to DC, bad regulator rectifier, right? So if you understand this concept, then you're going to work on some thing, motorcycle, some tractor, some whatever. They may actually, this may serve you well to understand. Make sense? The spinning part, if I were back up, all AC. This is all going to be AC production. After that, it should be converted to DC. Cool? and I'll show you on the next screen kind of how that looks. So the quantity of the voltage potential induced by an AC generator depends on, ready? So this is basically, in simple terms, voltage potential induced. So that's like how high the voltage is. Essentially, we could say how much power. How much power it puts out depends on strength of the magnetic field, the speed at which the magnet rotates, the relative distance between the magnet and conductors, the number of turns of wire, the stationary coil. All right, let's break that down. Starting with this one. If you want to make more power, you know what you need to do? Wind more times around that part. Wind more wire. You know the negative of that? Wire costs money and wire adds weight. So do they want to wind a whole bunch of extra? They're only going to wind as much as needed for that application. So let's just say you've got a Mercedes Sprinter van. And you're like, I'm going to go overlanding. I'm going to become a prepper. I'm going to do the fire movement. You guys have heard of that one? Financial independence, retire early, whatever. You could do all those things. That's cool, man. Go for it. But you buy this van so that it can be your van and your house. Make sense? Then you don't have to pay for a house. So you get this van and you're like, I'm going to put a big AC unit on there. I'm going to have my TV in there. I'm going to have like a heated blanket. I'm going to have all this microwave. You have all that. Well, if you want to power all that, how are you going to do that on the stock alternator, on the factory alternator, right? You'd have to have an alternator that puts out a lot more power. Make sense? You could have an alternator that has a higher number of turns on the wire. And by the way, some of those vans already come with the high output alternator, and it's bigger and heavier and more expensive. And it also a lot of times has different computer programming. Makes sense? So it's all designed. The engineers designed this to meet all the needs and probably a little bit extra just in case. Okay? But then also the distance between the magnet and the conductors. So again, the engineer designs that. Neither of these are something that we really have a whole lot of say in. Makes sense? Technicians, we don't do that. Engineer did that. Now the next one, the speed at which the magnet rotates, well, how the heck do you change that? How would you change that if you were in the driver's seat?
Rev it?
Yeah, rev it. This is engine RPM right here. And actually, it's technically a little bit more than that. We can actually determine the speed of rotation based on this pulley size. So they size this pulley to determine the speed. A bigger pulley will actually make it turn slower. A smaller pulley would actually make it be overdriven. It'll turn faster.
So that 1, 2, 3, 4, 5 depends on the size of the pulley.
What are you talking about? 1, 2, 3, 4, 5?
Yeah.
Not exactly, no. Your engine RPMs depend on how much gas pedal, right? The go-go juice. So you can increase the speed, and that's what you can do as a technician, I agree. But I did want to add that the engineer kind of sets the speed because they size the pulley. So if your engine RPM is 2,000, that doesn't mean your alternator RPM is 2,000 because your alternator's got a smaller pulley. So if the crankshaft is turning 2,000, it's actually going to probably turn your pulley like maybe 4,000 if it's half the size. Make sense?
Okay, so I control basically.
You do in a way. So let's say that there you are, you're in your van in the fire movement. You're like, I don't need a house. My house is my car, and I got all my electrical stuff and all my goodies. If you want to be able to power all that stuff, you could actually rev the van up to 2,000 RPM, and it may actually power everything you want it to power. Part of the reason that's critical is you think the alternator is going to make maximum power at idle. Idle might be 700 RPMs. 700 RPMs should be enough to make a certain amount, but a lot of our alternator test is at a specified RPM, right? So if you start the car in the morning, the idle might be 1,200, 1,100. But if it's warmed up, it might be 700, right? So they don't have us do our alternator tests at just any given idle speed, depending on conditions and temperature. They're going to say, at 1,500 RPMs, check this. Because the speed at which the magnet rotates has an effect on the amount of power. Make sense? So we have to actually set our engine RPM when we do these tests. Cool? So let's just say you're going down the freeway and you're at 4,000 RPMs because you're going kind of fast. Your alternator could make a ton of power. It can make a ton of power because it's turning a lot of RPMs because you're revved up. Make sense? And then the other one that we don't exactly control, but that's adjustable, right? These two are adjustable. The strength of magnetic field. How do you think that the alternator can vary that? If you guys remember last week, the strength of magnetic field would depend on really just like how much current flow we put through the coiled wire, right? So I'll back up one slide. If we were to put more current through this, we could actually field this to make a stronger magnetic field. That's going to make it harder for this magnet to move. You think I'm right? I'm right. If it makes it harder for this magnet to move, guess what? It's going to generate more power. But that's what's kind of weird. If it fields this and makes the magnetic field really strong, it makes this harder to move. What's going to happen to like your engine? It won't seize it, but it's going to put a load on it, right? So if you want more power, you can increase the magnetic field here. That's going to put more of a magnetic load on your actual engine, right? On your spinning alternator. If you ever hear when you first, if let's say the battery's dead and you jump the car and you first start up, sometimes the alternator actually make a little bit of sound because it's trying to run super strong magnetic field because the battery's dead. Right, so if the system senses, hey, the battery's really dead, let's increase the magnetic field, that's going to make it a little harder for the engine to turn, but it's also going to make the alternator put out a lot more power. Why does it need a lot more power in this situation? Because battery is pretty dead, right? Like if the battery was already kind of dead, the alternator's like, oh crap, the battery's dead, like field this thing, right? So kind of the reason that this is so important is the voltage regulator has a control on this, and if we were to go to even a more current one, the computer can look at the voltage and it can control the magnetic field on these.
So
go ahead.
Let's say you put a alternator in your car.
Yeah.
That's better than your engine. Can it mess up your engine because it's going faster than a better performing one? Or?
You're close. So I'm gonna bring it back to make sure it's all squared away. This has the ability to be, like right now, see how easy this is to turn? If your system is working correctly, and let's just make it computer controlled just for simplicity's sake. If the computer gives a signal to this, hey, the battery's dead, increase that magnetic field, I don't think you'd be able to turn this. Could your engine? Yes, but the computer controls that. So it's all on what the computer commands. The computer is not going to have that field so much that it stalls the engine because the computer is kind of looking at your engine RPM. I think though, if you were at idle and for some reason there was to be a malfunction and they were to try to send as much of a field as it possibly could, yeah, maybe it could stall the engine. But what we put on the car is always, you guys will start to understand, what we put on the car is what's supposed to be there. As soon as you want to know about, oh, let me put a bigger one, a better one, an extra one, or whatever, I don't always know what all the effects are going to be. So if we put an alternator that was not supposed to be on that car, what's it going to do? I'm not exactly sure. That's why if the customer were to ask, I just say, no, I'm not going to get involved in that because my job is to return the vehicle to like the original performance. Cool. So when someone comes in and they say, well, I bought the car this way, but I want it to act this other way. That's cool, but that takes like research and development and some testing periods and you know, what happens when it's hot and what happens when it colds and what happens when it's high elevation and low elevation. Like, I'm out. I'm out because that's not really what we're trying to do. So I would never suggest, if the car came with a 110 amp alternator and you wanted to put a 130, I'd say no. Could you do it and figure it out? I'm sure you could, but that's not generally like what we'd normally be doing. So let's just say, hypothetically, the alternator was 110 amp. 130 amp might have a smaller pulley, but it might be a bigger body because it might have more windings on there. You remember how it would say that increase the number of windings? It also may have a smaller pulley to increase the speed. It may have a tighter distance right here. And it might have a stronger magnetic field, but usually this one's controlled by the computer. So I don't really know. I guess if you were to buy like the Sprinter with the basic alternator, the computer's programmed in this way. And if you were to buy the one with the 150 amp alternator, the computer's probably programmed a different way. So what would it take to change it? Probably more than just a different size belt. It might actually take like an ECU program. So that's going to take a bunch of research, but you guys get the point. We can change the alternator's output by redesigning it differently, or even potentially by programming the computer, or simply by increasing the engine RPM. So what I've seen in the field was, like, for example, a fire truck that has, it's a diesel, and it has a big electric pump that runs off big old battery terminals, big strong battery terminals. And what they did was they installed this system where if they ran the pump would send a signal to this little computer that they added. And that computer was plugged right into the OBD2 connector. And that would send a signal to the engine to say, idle up. So if they started running their big pump electrically, it sent a signal and automatically the engine RPM would go up to 2,000, whatever. And that was using the factory alternator with just like a manual override to bump the RPM up to give the alternator as much power as it needed to run this big pump. Make sense?
It's like if you have a food truck, basically that when it idles, that's what the alternator is.
Oh, it was probably designed for that. Yeah. So if you pull up with your food truck and you want to have your lights and all your stuff on, you better have it running. And then that food truck should have been designed to run all of those different items at either idle, or if it can't run it at idle, something should be in place where we could bump the RPM up to be able to run all those items. Otherwise it'd be dead. The other way you could do it, let's say it's like an RV, you just don't rely on the alternator and you put in a generator, a standalone independent generator to power all your electrical stuff. Your generator works basically the same as your alternator, except you don't have to rev the regular vehicle engine. You could actually have the generator engine go up and down all on its own, right? But that's kind of the concept. Now here's the AC. So if that thing is turning kind of slowly and it was what we call a single phase, you have AC current. Remember when it was side to side, it doesn't make any current. When it's up and down, it makes a maximum. Or it might have been the other way, I forget. So it's always going up, 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 and then down, and then it'll actually go into negative, and then back to zero, and then to positive, and then back to zero, and then to negative, right? So this is alternating current. This is a waveform of AC. If we were to say, let's make this 20 volts right here. It was 0 volts, it was 20, it was 0, it was negative 20, it was 0, it was positive 20, it was 0. That's kind of all over the place. Can you imagine trying to run power off of this? You have no power, you have power, you have negative power, you have no power, you have power. Like you see how choppy this is? There's a big gap right here. All of this right here is not enough power. So here's what we'll do. We'll take this, and then we'll add another phase and another phase. So you actually have the same thing, but you'll do it 3 different times. See how this one was blue? The blue one's still here, right? But look what we did. We started a yellow one a third of a cycle later, and the yellow one does the same thing. And then a third of a cycle later, we started the red one. And the red one does the same thing, but see, they're all a third off. Makes sense? So if you have all of them a third off, look, you've always got really good power right here. See that? Right here, you had power, no power, negative power, right? Here, you got good power here, and also on the negative side, you got good negative. You got good positive, you got good negative. So this is something that's called three-phase AC. AC always looks like this, but if you want it to be a smooth power delivery, you want to do it with three of them. One's just starting a third late and the other starting a third late, right? So if there's three phases and you have all three of them, that's your full cycle right there. So if you were to look at that in rotational form,
Is it always in third phases?
if there's three phases, yes.
There's more than three phases.
Well, technically you could make as many as you wanted, but we don't.
So you can program it. So
No, not really. This is a physical part in here. There's actually three rotating parts. There's three circuits, right? So if you were to look at this one right here, how it's up and down is making like maximum. But then as you turn a little bit more, it's making nothing. As you turn a little bit more, it's making maximum. Well, we would do that 3 times. So while this one's at maximum, that's phase 1. The next phase would be like more like right about here. So it's already gone past maximum and it's starting to get a little bit, it's starting to come around where it's going to be maximum again. And then your third phase would be over here. So one of them is always about to hit their maximum. Makes sense? But you'd have to have 3. So you'd have 3 magnets and 3 sets of these coils. Now, if you remember, if there's 3 sets of these right here, there's 2, right? So if there was 3, you're going to end up needing 3 of everything. So that would be actually 6 of these and 3 of these. Kind of makes sense a little bit. The only real reason that we do that is just to get this to be smooth. One was too choppy. One was not quite, one wasn't consistent enough. Cool? So we give it 3. But imagine if we took 3 phases and we all start them at the same time. Then you'd have 3 of them making a ton of power, and then all of them making none, and then 3 of them making a ton of negative. That doesn't help the cause. Makes sense? It doesn't fix it. So we spread them out. We start them a little late. If this were to be, let's say, you guys exiting that door, if you were to all try to go out the same time, that wouldn't make a lot of sense. So how could we make it smooth? One goes, one goes, one goes. Make sense? There's 3 people. You don't need them all to go at the same time. You'd wait a little bit and start the next one later, and then wait a little bit and start the next one later. But this is showing it in time. The reason we don't say like, let's say 9 o'clock, 9:05, and 9:10 is because the alternator doesn't really, time doesn't make a whole lot of sense because it would depend on the speed, right? So the faster it spins, the time would have to be less, right? So we measure it in an amount of rotation. So remember, it's a third of a rotation, right? That's why right here, I'm going to do a little quick drawing on here. If let's just pick, let's say this one. This would be phase 1 right here. And red's kind of okay, but let's see what other markers I got in blue. Here's 1. Then we'd have to have another magnet like this. And this would be 2 down here. Then we'd have to have yet another magnet like this. And this would be 3. Okay, so if you were to look at it, you'd always have 1, 2, and 3, and they'd always be making their maximum power, or pretty close to their maximum power. So there'd be 3 of them spinning, and then there'd be double, 3 of these. So 1, 2, but you'd have that actually 3 times, so there'd really be 6. Kind of sort of makes sense? So inside of that alternator, there's actually this, except 3 times. Boom, boom, boom. And they're constantly making close to their peak power. But they all start a third later in the rotation. So you guys kind of understand rotation in degrees? If it started here and it went here, and then went here. If you actually look, from south to north has gone a full rotation. Would you agree? It was south up, and it did a full spin, and it's back to south up. How many degrees did that turn?
360.
Exactly, 360. So if you were to think of a 360, what's a third of a 360? Do you know the number?
180.
180 is a half. Two 180s become a 360.
90.
And 90 is a fourth. So if there were 4 phases, to be honest, 4 phases would be simpler, because you'd be like, this would be phase 1, this would be phase 2, this would be phase 3, this would be phase 4, and they'd all be 90 degrees after each other, but which would be a quarter of a cycle. But we're at a third of a cycle, so it's more than 90, but less than a half. It's a 120. So in angles, we'd start, let's say, 1 at 0, 1 at 120. What's 120 twice? 260, right? So a 0, a 120, a 240, sorry. 0, 120, 240. They're all starting at different angles. And they're all spinning together, but they're 120 degrees off. Kind of? Sort of? A little bit? Okay, as much as you need to. And again, I think the animation is going to really, really help. Okay? So now when we look at this, you can see the rotor. The rotor rotates. And this is what it looks like, right? Pop it right up on there. That's going to be all inside the housing. And then if you look, the stator right here, these are actually windings. So these right here are magnets. These are electrical windings. The reason we go into the 3 phases is because this looks like there's a ton of winding, and there kind of is. But at the end of the day, there's really only 3. So there's phase 1 phase, 2 phase, 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Those are all wired together. So phase 1 is going to occur a whole bunch of times. Phase 2 is going to occur a whole bunch of times. Phase 3 is going to occur a whole bunch of times. So as this is rotating, let's just point at one of these magnets. When one of those magnets cuts through the magnetic field of phase 1, it's going to produce a peak for phase 1. And then as it continues, it's going to go low, and then it's going to go high, right? So that's that sine wave we saw. But the thing is, we're going to have a lot of magnets. So there's a lot of them doing the same thing all at the same time. You have 3 phases constantly in production, and that's why we have all these magnets and what appears to be like a bajillion different windings there. Okay, so it's kind of weird. Why do you think we do that? Who thinks they know why we would do so many? Why don't we just do one? You saw that one would work, right?
Because the more you have more power.
Exactly. That's exactly what it is. That's right. So yes, the more that we have on there, and by the way, the bigger the magnets are, the stronger the magnets are, that's making more and more power, right? So we just talked about how we need so much electrical demand on the modern vehicle. We'll have tons of these in there. Now here's how it kind of works more like for a technician. We don't calculate that. We don't design that. We don't do the math and talk about the left-hand rule and the right-hand rule. And what we really do is we're going to diagnose the car. So if you rolled up to this vehicle and this vehicle had a charging system problem, as evident by like the battery light is on, or the battery's dead and you jumped it, but you pulled the jumper cables off and it died, you know the charging system isn't working. Inside the alternator, you should know if there was something wrong with these magnets, that could cause it. If you had an issue with this pulley, that could cause it. If you had an issue with the windings here in the stator, that could cause it. All those windings are going to come together and go into the voltage regulator. That could cause it, which also rectifies. So rectification is when you would erect a building, you'd stand it up. The voltage regulator and rectifier takes your AC, goes into the regulator rectifier. Using diodes, we stand it up into DC. So this could fail. That also controls, the fielding of the coils. That could fail. All these things could fail. But wait, that's not all. What do you think these are? Bearings and bushings. Could that bearing fail?
Yes.
Heck yeah, and what would be the symptom if it did? And what's the customer's going to notice? Probably noises to start, and then if they keep on running, this will get more and more loose, and then this magnetic rotor can actually start to tilt, and that rotor might actually have an effect on the magnetic field. It might get so loose that it could actually contact the the windings in the stator, right? So you could have like 100 different failures in an alternator. But one of the most simple ones is the alternator makes noise. Alternator bearing that's bad could make a lot of noise. It could still charge the car though. It could still generate all the power it needs. But if that bearing is failing and you're hearing a noise, it's going to be like, well, you really need to replace the bearing. But this is the simple aspect. Similar to starters, you all and me, our labor is too expensive. So we're not going to be like, yeah, go ahead and pay me a couple hours to take your alternator apart and pull this apart and get a bearing and press a bearing in and then clean it, reassemble it, whatever. It's probably not going to be 2 hours. It's going to be more than that. And the problem is for a shop to run a business, they're all way over $100 an hour around here. So you're going to say 2-3 hours of labor to do that bearing, right? You can go buy a remanufactured alternator for $300. Why would we try to fix a bearing for $300 when we can buy a remanufactured for $300? Now, why is the remanufactured so inexpensive from the parts store? That's the big question. It's used, but somebody's gone through and fixed it all up. Why are they not charging $100 an hour? It wasn't here.
It wasn't.
It was. Oh, you mean it wasn't remanufactured?
Oh, no, it was done, but it wasn't done in the U.S. It was sent probably to Mexico or maybe, somewhere. The only reason they don't send them to China is probably because it's too expensive to get it there and back. But generally, we're not really remanufacturing these, right? They're going to pay somebody, remember these guys that I talk with and fix their cars, I know some of them were doing construction in Mexico for $15 a day. You could do a whole lot of alternators in a day for $15. So if you're going to send it down there and they're going to remanufacture it and then they're going to spray paint it and send it back, what we're going to do as technicians all day, take this one off, put the remanufactured one on. Hope the remanufactured one is done well, and that's why I like to go a little bit above and beyond and say, you guys got to understand what's in here. Not that you're going to remanufacture this, but you're going to have to diagnose this. And when you get a remanufactured one, some of them are going to be no good. I've put them in before and had them last a week and had them not work anymore. And then I'm looking at it like, well, what's up? The good news is, generally like O'Reilly's, AutoZone's, Napa, they got a warranty, right? So if it fails, what do? Just take it off and bring it back. Now the irritating part to me is like, what do I do with the customer? The customer's like, hey, it failed and it's only been a week. And I'm like, O'Reilly's, what's the deal? Auto parts like this. And I'll go back and I'll say, hey, I need a new alternator. And they'll be like, oh, no problem. Give us the old one and here's your new one. And I'm sort of like, you going to come put it in? Or because now I'm fixing the car again for free. So it is kind of irritating when
Would they be able to check it though before selling it?
Yes, they should, and they claim they do. But this particular,
Can they run them for a bit,
They can. They can, but they're gonna maybe run it for just a minute.
Right.
They're gonna run it for a few seconds and be like, yeah, it works. Bada bing, bada boom. This particular one I recall was in a GMC Acadia. It had some ongoing issues. I put it in. It was running good. Everybody was happy. A week later, hey, my battery light's back on, and I'm like, la luz de pila, right? And I'm like, oh my gosh, you got to be kidding. That alternator is remanufactured. See, I thought about getting him a brand new one. The brand new one from GM was like $600. So the O'Reilly's one was like $200, and I'm like, yeah, Tomas, we'll get the O'Reilly's one. It'll be fine. A week later, the light's back on. I ran through and did my rechecks. It had everything it needed, which we're going to talk about. And it just put out no voltage. It was just running purely off the battery. Now the car doesn't die instantly. That's what's interesting. He drove and the battery light was on, and he drove a little more and the battery light was on. But it was like, no, just let me come over there with my jump pack. I put my jump pack on it and I drove it to my house with the jump pack on it so I didn't have to change it in the dirt again. The first time was in the dirt. This time I said, no, I'm bringing it to my house. And I'm gonna work standing up. So if something fails on the reman, you have to kind of have an idea of what's going on in there, right? So if it's a noise, maybe a bearing. If it's not charging, it could be something with the windings, but the main point of failure is either gonna be in the regulator rectifier, or you're going to see it's not really well shown, but there has to be a slip ring and brushes. This actually shows it kind of well. And in fact, right in here, this one's a cutaway. there's a spinning part and those brushes have to ride across there. So we can have a failure on that part pretty commonly. And that's one of the main things that needs to be addressed when they remanufacture it, right? So knowing a little bit more is going to be helpful. Cool. Okay, and then like we were already talking about, remember how we can change the power output based on the strength of magnetic field? Well, that's what it's saying. The amount of current that flows through the rotor field coils, so those field coils that were on the sides, we can change the amount of current that flows through them. The more current flow, the stronger the magnetic field. And you can hear the alternator will kind of like maybe start to make a little sound. The engine may dip for a second, but on a fuel-injected vehicle, because the engine RPM is controlled by the computer, if the engine RPM dips, the computer is going to say like, hey, bring that RPM back up, and it'll just open the throttle a little bit more. So you might not hear all that much on a modern car, but like on an older vehicle, if you were to field this alternator full, a lot of times the RPM would drop. Like if it's carbureted, the RPM would absolutely drop. On a computer controlled, no, it'll bump the RPM up to make up for the added field and the added force required. Cool? All right, and then the regulator switching takes place in milliseconds. So what that means is like when this is spinning and we're regulating and we're rectifying, it's going to do the switching so fast, you really can't even tell. Like you can't tell, it's hard to even measure. It's just going to put out a really nice clean signal. Now the regulator in a modern vehicle is solid state. What do you guys remember about solid state electronics? No moving parts. It's not like a relay. It's in a way, the simple version is like it's computerized. So we can use diodes and transistors, and that can make the switching super, super fast, really clean, smooth output. If this were a generator that you would buy to do like a house backup, we could say this is a pure sine wave. We can make it like a really nice, clean, smooth wave. Now generators are trying to generate AC for your house, so it can do like a beautiful, pure sine wave. For a vehicle, you know, we're trying to make DC, but it's just saying we can make a nice, smooth, crisp DC current output. Really nice. Now, how do we control that though? So if I'm saying this is solid state, and that's what's going to rectify and regulate the voltage. If this is solid state is controlled by other solid state. You know what the other solid state is? An electronic device that controls the rotor field current with a pulse width modulated signal. What the heck? Pulse width modulated signal? Oh, you know what works with that? Computers make that. So basically, if I were to translate this for you, it's saying your regulator rectifier is kind of computerized, and it's controlled by the computer. So on your vehicle, you know, you have an engine computer, right? An ECM, if you will, engine control module. Engine control module will control the regulator using a pulse width modulated signal. Now, we're going to come back to that, but just understand, this is computer language, computer lingo. Make sense? Old school, mechanical, new school, computer control. Okay, we'll come back to that pulse width modulated signal. And then look, you guys can see what's wrong with this vehicle.
The battery lights on.
The battery lights, so what's that tell you?
Charging system.
Right, is it the alternator? Is it the wiring? Is it connections? I don't, maybe. I don't think it'd be a bad battery, because even if the battery's shot, the alternator should be able to still charge the system. However, I have seen in some instances, if a battery is sulfated and shorted, it could actually itself be kind of shorted and pull the charging system down with it. So, you know, this is the point is this is going to take some diagnosis. It'd be a really good idea to check the battery. How would you do it?
Multimeter?
The meter will tell you if it's charged or not. How are you going to check to see if it's sulfated? Remember those? Remember how we did that test before? Battery test. Remember the battery tester? You can do that. It'd be a really good idea as part of your diagnosis to make sure the battery's not severely sulfated or really, really bad. Makes sense? But generally, we got an issue with the charging system. Maybe it's a regulator rectifier. It used to be mounted on the fender, But on a newer one, the regulator's electronic circuit senses the battery voltage and switches the rotor circuit on and off rapidly. Yeah, that type is going to be built into the alternator. This regulator rectifier right here says Bosch. This is the main control for the alternator. However, this needs to be told what to do. This is computerized, but not necessarily like a communicating computer. So if this controls the magnetic field in the alternator, who do you think tells this what to do? I told you once. Exactly. The ECM. The battery doesn't think. The battery just stores. So the computer is going to say, hey, you know what? I measured the battery voltage and the battery voltage is low. I'm going to send a signal right here and say, increase the magnetic field. Now the signal that it listed was pulse width modulated. Do you want to know what that means? Pulse width modulated. Okay. I'll give it to you in a simplified version, right? So if we want to tell that computer what to do, we're going to give it an on-off pulse. Okay. So I'm going to do this right here. Let's make this on up here. Let's make this off down here. Let's say your battery's fairly charged. We want a lot of off time. And we need just a little on time. How's that look? That's just a little off. So we might have, I'm going to switch it's pulse width modulation, which actually measures these distances. But I'm going to switch it to something called duty cycle. Let's say we have a 10% on and a 90% off. That would be like 10% duty cycle. That would be very little pulse width modulation. Make sense? So is this going to charge a lot? It's only on 10%, it's off 90. That's not going to charge a whole lot, is it? Okay, so the computer is going to send this signal out. Now let's just say your battery is kind of dead. Let's change it from 90 to how about how much would you say that is? What if this on time, exactly, is the same as this off time? Let's say we have 50 on and 50 off. Do you know what that's going to make the alternator do? Charge at half capacity. That's going to charge at half of max. So if you have a bunch of electrical components running, the computer can sense that. The computer is going to see your voltage is starting to drop a little bit, and it's going to say, hey, you know what? Bump it up from 10 on to 50 on. Cool? Bump it up from 10 milliseconds to 50 milliseconds pulse width. Does that make sense? Computers are kind of nice like that, huh? All right, now let's just say your vehicle, the battery was totally dead. Totally dead. And the computer knows it. What do you think the computer is going to do? How much is the on time going to be? 90. Maybe 90, yeah. How much is the off time going to be? Maybe 10, yeah, because it's a percentage, so it's always got to be proportional, right? We could do a 90 on, we could do a 10 off. Sometimes you might even be able to do like a 99 on. I don't know, in some cases they can run 100, right? But the point is, remember how we were saying we don't want to overcharge it. Did you agree with that? We don't want to overcharge it because that wastes electricity. That wastes gas because remember the engine is turning the rotor. Cool. We only want to charge it how much it needs it. So the computer is watching very carefully and saying, hey, you know what? I think I need to increase it to 90. And then if your battery starts to get charged, once your battery's charged, what should this start to do? Shorten, back off, back off, back off. And if you're on the freeway cruising and your battery's all charged and you're not using that many accessories, maybe it should drop even below 10% duty cycle or 10 milliseconds of pulse width modulation. Makes sense? See how this is more efficient? We couldn't do this until the computer was part of it. Now, my point in explaining all this in detail is, you remember this regulator rectifier doesn't think it does what it's told. So now I ask you again, what's telling this what to do? Exactly, the computer, and how though? But how?
By signals or
Exactly. So if your system, if let's say your alternator is not charging and you're like, oh, it's an alternator. If for some reason a mouse chewed your wire right here, it would never show the 90. Do you know what it would show?
the 10.
It wouldn't even be the 10. It would just literally show off all the time. It would be 100% off. So how much is it going to charge? It's not. So what if your ECM isn't sending the correct signal? Or what if your ECM sent the right signal, but that wire that goes to this regulator got chewed, is loose, the terminal's messed up? Here's one that's really simple. It was pretty fun when I was a kid. It's fun to look back because I really didn't know anything. Like, I was into cars, and if you asked me like what that car was, I could tell you what it was, what year it was, what engine it was, but I really did not have the skill set to diagnose cars, so you know. I wasn't born that way. So I remember we were on a trip, it was actually a youth group trip, and this guy who was carrying a bunch of kids, like, we were looking in the rearview mirror, and his lights were going from like white to like kind of brown and dim. And I remember the guy driving the van was like, Ken's headlights look weird. And I remember looking, being like, oh, it looks like his battery's dead. And I was like, wait a minute, we're driving. How's his battery dying while driving? Follow my logic. What do you think? The battery's draining. How's the battery draining while he's driving though? It's running. It's not charging, right? So we pull over, we go back there, and they kind of ask me, and I remember so many conversations in that van. There's a noise, and they're like, what do you think it is? And I'm like, I don't know, maybe it's the transmission. And they're like, I think it's the fan belt, right? Nobody knew anything in that van. We all needed to just be quiet and pay somebody who knew, okay? But we talked about it, we pulled over, we go back there, and the guy gets out of there, and he's like, man, I just put this alternator in. And I'm thinking like, oh no, it's bad. And then remember how there's a little wire from the computer that gives the signal, right? He looks down, there's like, oh, I forgot to plug that in. Click, plugs it in, and all of a sudden, the lights start to come back up, the battery comes back up, right? So why did that alternator not charge?
Because the wire wasn't plugged in.
The one wire that wasn't plugged in is the one that gives that the signal. That was the wire that gives that pulse width modulation signal. It was disconnected. The computer's like, charge, please charge. And the alternator's like, huh? I'm just chilling. It wasn't getting the signal, right? So when we do our diagnosis, that's why you want to understand that pulse width modulation or that duty cycle signal. You got to make sure it's getting that. If it's not getting that, it isn't going to charge. And you can put a new one and another new one and a remanufactured and go on Amazon and you can go to the deal. You can put as many alternators as you want. If it's not getting that signal, it's not going to charge for sure. Cool? All right. And that's kind of what it's saying. The alternator regulator functions built into the powertrain control module, ECM, PCM, or whatever. The computer has a strategy. The computer is programmed for how much pulse width modulation or duty cycle to send based on the voltage, based on all your electrical loads, right? This is all computer controlled. A cool thing is, you guys remember when we plugged in the scan tool and tested some switches? A cool thing is, on some of those, you can go in and you can manually tell the alternator to charge 100% and see if it responds. So that's kind of, you can override it with the actual scan tool. So there's some nice things you could do. And again, the output voltage is controlled by switching the rotor's field circuit on and off, right? So remember that symbol, remember that signal, right? If we got a 10% on, this receives that 10% duty cycle, and it's only going to command the magnetic field on 10%. If you want it to be 90, the computer has to send a 90% duty cycle or a 90 millisecond pulse width, and then this will command it on 90%. That'll increase the field, right? So this does control the magnetic field, but this part here doesn't do the thinking. The ECM, the powertrain control module, the PCM does the thinking and just controls this with one little wire, just one little wire that has pulse width modulation signal on it, okay? That's kind of the point. The computer, the PCM can make adjustments. Most of the time, alternator is controlled by the PCM. Sometimes they may control it with some other module, but if it's a newer car, it's going to be computer controlled. Computer controlled, computer controlled. If it's an older car, by the way, not so much. They had a mechanical voltage regulator, and that would just get a signal of battery voltage. And what it did with that battery voltage was if it was low, it would field the coils more, and if it was high, it would field the coils less. It was much more mechanical. But it's been like this for probably 20 years plus, maybe 25, maybe 30. It's been a while. Okay. And PS, if it has a problem related to the charging system, the PCM can actually store codes. So remember, I remember somebody was talking about a bad starter alternator or something. Actually, the scan tool is a good diagnostic tool Plug it in, see if there's any codes related to the charging system. Sometimes the computer monitors that wire that gives the signal, and if it's open, it'll actually set like a, alternator, pulse width signal control circuit open. It'll set some sort of code, and you'll be like, oh, if that's open, maybe I need to inspect that wire really well. Okay, pretty cool. All right, and then remember when we talk about rectification, that's just the way that it takes the AC and stands it up into DC. All right, and then these rectifiers generally are in this rear housing. Back in the day, they might have been actually separately, remotely mounted. And so remember what a diode does. It allows current to flow in only one direction. Is that fair? So you remember how the AC current would flow this way? Then what would it do? It would try to flow back, right? But what if there was a diode right here? The diode would only let the AC flow this way. When it tried to flow back out of the alternator because the alternator is producing AC, it would stop it, right? Do you understand how that could make it into DC? It would let it flow this way, it would stop it, it would let it flow this way, it would stop it. Guess what? You just made DC out of AC. Cool? Remember, AC alternates this way, this way, this way, this way, this way, this way. One diode can make that into DC, but you got to remember there was 3 phases, right? So if we have 3 phases of alternators, that means we're going to actually have at least 3 diodes, and there's really going to be 6 because there's the way that it's wired. We got it producing a positive here, and then a negative, and then a positive, and then a negative. Well, these diodes are going to be built into a bridge, and basically 3-phase AC is going to come in, but after those diodes do their job, only clean DC should come out. Okay, make sense? And then if you'll remember, one side of each of the windings connected to one of the bridges. So you got 2 sides of each phase. You got 3 phases, and so there's your 6. That's why we would have 6 diodes in there. Here's what that would look like. Okay, and this one gets kind of crazy. But this is your rectifier bridge. So this has your diodes. What do you think these weird, like, fins are for? We have fins here to catch air. Why do we want air to contact that? Yes, exactly. So it doesn't overheat. So when we want to do that rectification with the diodes, it makes heat, right? Because the diode's kind of like a load in the system. So if it has heat right here, we need to cool this to keep it cool so the electronics don't burn up and fail. That rectifier bridge is built into this alternator back here. You ever notice your alternator has all these little holes, right? If you ever notice when you spin this, you'll see that there's a little fan, sometimes in the back and sometimes in the front, but in this one, it's definitely in the front. If you spin that, this is a fan. As your engine's running, this fan is blowing air through all these coils of wire and through that rectifier bridge to keep it nice and cool, at least as cool as possible. So this is going to do the rectification. What that looks like on a diagram. Now you remember these? Look at the angles of these. Remember we were talking about degrees before? Look at this. 120 degrees, 120 degrees, 120 degrees. So phase A, phase B, phase C. And so these are the coils. As this is going to spin, we may spin this around. Let's just say it induces a voltage in coil B, stator coil B. That's going to send it down here, and it can go out right here. It can't go back this way. It can only go the way that the diode allows it. Cool? So that's going to go to the battery. Then as this continues to spin, actually the south coming up may try to provide a negative. And so this is constantly going to make sure whatever is produced is going to come out this side, DC only, even though this is actually going to try to make alternating current. See, so these are going to make alternating current, but by the time it goes into the regulator rectifier, if it's trying to go back this way, it's going to be a no. If it's trying to go this way, it's going to be a yes. So therefore, anything coming out is no longer AC, it's all DC. Kind of makes sense, sort of? So this is called rectifying. Tell it back to me. What's rectifying do? That's it. All right, and if you didn't really care to know all these little intricate details, you'd just be like, well, the alternator should put out DC. And that's probably, technically it does alternate, and that's why it's alternating. It is AC, but by the time it goes into this rectifier bridge, it should come out DC. But kind of the interesting thing is, if you have a problem over here or over here, they're both in the alternator. Your remanufactured alternator comes with both, so who really cares? But because you guys are here, and I'm trying to get you to the next level, how do you think you diagnose if it's here or here? I gave you a clue of this earlier. Remember I was saying how I would diagnose the motorcycle? I would actually try to see if 20 volts AC is coming out of all three of these. Let's say on A, I got 20 volts AC. On B, I got 0. On C, I got 20 volts AC. Is my problem here or here? Right in here. So you'd be like, oh, it's in this part right here. So on a motorcycle, this is in the engine case. And then 3 wires leave it. Here's the 3 wires. And they go into this box right here, which kind of looks like this. And that's what rectifies it. So if I have 3 good, clean AC signals or AC power coming into this rectifier, but this rectifier isn't putting out a nice 13.5 DC, then I know it's the rectifier, right? So I need to make sure it's getting the AC and see if it's turning it into DC. Cool? And that's it. And on a car, we don't even necessarily separate the two. In a car, what we really need to do is make sure the big battery cable's good and make sure it's getting that pulse width modulated or duty cycle signal from the computer. And if it is, and the belt's not ripped off of it, it's the alternator. Okay? So this is just kind of like a summary of what I had just explained, right? Because we have those, that coil rotating, and it's going to constantly be sending AC into this rectifier bridge. So now let's discuss these diodes a bit more. You guys remember, diodes allow current flow one way, right? What if one of these diodes were to be internally shorted and they were to start to allow current flow not only out, but like back in through? What would this alternator start to produce? It wouldn't be just DC anymore, would it? It'd start to make AC. There's a test when we do alternator test called diode ripple. If one of these diodes is shorted, where it allows both to the right and to the left, I agree, the voltage is going to fluctuate, but we could actually measure that as AC current in the system. If you have AC current in the system, it doesn't work real well with DC stuff. That can cause all sorts of trouble. So we would go ahead and we'd put our alternator test on there. It's the battery tester typically. It's usually a full like battery starting charging system tester. One of the things it looks for is actually AC to be flowing in the system. If you have AC coming out of your alternator, you know that one of these diodes is shorted and it's allowing current out and back in. Make sense? If one of those diodes is bad, what do you think we should do? That's right. Nobody for replace the diode, because we don't do that. Technically, though, we could if it had that regulator if it had that rectifier. If you wanted to go in there, you could replace the rectifier. But I go into the parts store and be like, "Hi, I want a rectifier bridge for my modern vehicle." And they're gonna be like, "You want a what? I don't see anything in my system. There's nothing in my system." They don't know what it is. They don't even know. It's inside the alternator. They sell the whole alternator. You can't get the parts inside the alternator at a typical place. Somewhere, maybe you can. Online, maybe you can. Make sense? Now you guys can kind of get a little bit of a picture of this. Now, what if one of these diodes were to not be shorted, but were to be open internally? What do you think would happen? Let's just say when this comes around to stator coil B goes down to here and it tries to go through this diode, but let's say that diode has an open. Is stator coil B going to produce any power in that moment? No. Exactly. So what would that cause the alternator output to be? Low. Yeah, like a third. Like it would lose like a third. That's basically the same as if stator coil B was burned up and if stator coil B rectifier diode was burned up, right? So if one of these fails, your alternator might put out like a third of the power. So let's say your alternator is rated for 120 amps. If one of these is bad or one of these is bad, how much is it going to put out?
0.
Not 0, because A will still work and C will still work.
Oh, it's
A third. So we should get 120. If we lose a third, how much is that? It might only make 90. Am I right?
Yeah.
No, that's not right.
60.
3. Actually, that's kind of interesting. Let me make a new number. Let me make it 90. There we go. Let me make it 90. If we lose a third, how much? So it lost 30 and it's only making 60. So when we do our amperage test and we field it and we do all the correct stuff, if we're expecting to get 90 amps and we only get 60, is this alternator good or bad? It's bad. Is it because of this or this? It kind of doesn't really matter. If we had to diagnose it, we'd see if we have AC coming out of stator coil B, and then see if we have DC coming out of stator coil B rectifier diode. But see, we don't actually have test points for that. So in a vehicle, you're just literally going to see how much power is coming out this big wire. And if it's 90 and it's supposed to be 90, you're chilling. And if it's 60, but it's supposed to be 90, you're not chilling. It needs to be replaced. Make sense? Kind of? That would be a really easy diagnosis, because if it can make 60, you know it's getting a good duty cycle or pulse width modulated signal from the computer. You just know it's low output, which is like, okay, your alternator's no good. What do you think the customer concern would be if it was to only make 2/3 of its output? Because the car would probably start and run. Car would be good, but under high electrical demands, I'll keep going back to that power steering. That electric power steering, trust me, it needs all that alternator can give. You might actually get it like a power steer. When you go to turn the electric power steering, that battery light may come on for a quick second. And then when you straighten it back out, the battery light may go off. Because only on the most demanding of demanding situations is 60 not enough, and it needed the full 90. Make sense? So like Priscilla was saying, her light comes on sometimes, yes and no. Now I have a feeling that thing may have like a big old subwoofer in there. I don't know, I'm just saying, if it did, when you're doing the subwoofer, boom, 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 A, you're getting brain damage, ear damage, but also you're asking that alternator to give everything it's got. And if exactly. And so you might actually be exceeding what the alternator's limit is. However, if the alternator lost a third of its output, you may really start to see that battery light come on more frequently, right? So we'd have to do some tests. Let's see how many amps come out of that alternator, and then you'll know. You'll know what you got. Cool. So that's kind of what this is showing. Like you had the 3-phase AC. Cool. You can tell, right? Because it's positive to negative. Remember, the diode is not going to allow it to flow down. It only allows the flow up. So if you look after it's regulated, after it's rectified, I mean, look at this. You have nothing below 0, do you? And if you look, you actually have a pretty clean voltage up here. That's because it's all been rectified. So coming out is this, going into the rectifier this, coming out of the rectifier should be this. If one of these diodes is bad or one of these phases is bad, let's say you lost the whole red line, it would have too much ripple, right? It'd be everywhere where the red was supposed to be, it would have a big ripple. That's what your tester is testing. Like it's testing for ripple. The ripple is going to tell you maybe you got a bad diode. It could even tell you if it's got too much ripple that it's got one of the coils not producing. Make sense? So it should be clean like this. If it's, that would be like it's lost 1/3. Cool. And then if you look, here's the components cut away like we were talking about. The belt, the fans right here. See this fan? This fan's going to blow air through there. The rotor spinning, those are magnets. And then here's the field coils on the outside, and they're in 3 phases. Now in the back, we have this thing I mentioned once called a slip ring. Because remember, we have to make a connection to this. So if this is spinning, we have to actually make a connection. So we'll have a slip ring, and we'll actually have a brush that rides on the slip ring. And that depends on the design. There is ways to get rid of the slip ring design, but we're going to have a brush on there, and those brushes are typically a failure point, right? So we probably won't normally get down to this level, but at least you can kind of see the components. What I don't want you to do is not know kind of what's happening in that alternator, because that's going to make your diagnosis probably wrong. Okay. Overall, should be pretty good. I think we're probably pretty good on there. And you guys can see, what's the rotor do, by the way? Exactly. So when you see the belt go to a pulley and this goes to some sort of like a shaft, you know that's going to the rotor. Cool. What if you were to have this belt damaged, and let's say the belt broke off? You think you're going to have it charging? It's not going to charge. So sometimes people even say, I think I was driving and all of a sudden I heard a noise and my battery light came on. I think I need a new battery. It's sort of like batteries generally don't even cause the battery light. That's more like a charging system. Oh, then I must need an alternator. Well, maybe, but if the belt's off the car, guess what? Your red battery light's going to be on. Why is it on though? If this doesn't spin, it ain't going to make no 13.5 volts, right? If this stops spinning because the belt comes off, the rotor doesn't spin. If the rotor doesn't spin past the field coils, it doesn't make any AC. If it doesn't make any AC, it doesn't get rectified into DC, and your battery, basically your whole vehicle at that point is just running on your battery. And you can, by the way. If you wanted, you could take the belt off and drive around for a while. If your battery's fully charged, it's 12.6, right? Well, as you drive it, the power for the coils, the power for all the things you're running, including the power steering, right? That's all going to be drawn off the battery. So your battery goes from 12.6 to 12.5, 12.4, 12.3, 12.2. It will keep running for a bit, and then it'll be so dead where it won't fire the spark plug anymore, and then you're done. And the computer's shut down. So it's kind of interesting. All right, probably pretty good. Okay, and then on some of the older ones, they're a bit different. So the rotor, like especially on an older vehicle, remember the rotor spins, right? There's different ways to do it. We could use this rotor. That one sounds really good. Something's up with that. I think that's actually the slip ring. So if this rotor were to be spinning, you guys could imagine if we used a permanent magnet rotor, we don't have to send any current in there. Make sense? Because they're already magnetized. But back in the day, we'd use electromagnets for the rotor, and that's when we'd have to send a positive and a negative in there to get the electromagnet to magnetize. And that was one of the times that we would use diodes, and we'd use the slip ring and the brushes. They call this self-exciting, and it can only happen when it's putting an output, when it's producing an output. So if it's on an older vehicle, it may be self-exciting. And this was kind of self-contained because all you really had to do, you'd give it positive battery voltage through the ignition switch. So as soon as you turned it on, it would get a signal from the battery. That battery voltage would do self-excitation, and basically it would know how much voltage to put out on its own. Can it make sense? It doesn't have a real accurate way to not overcharge or undercharge, but it would self-excite and it would produce, I don't know, 13.9, let's say, 13.9 volts. When you were going down the freeway and your battery was charged, it would still put out a whole bunch of amps. This was inefficient. So how do we increase the efficiency, increase our fuel economy, lower our emissions? We get rid of this. And then we would go to the computer controlled. That's the more modern one. So here's some of that older stuff, the diode trio. You can see there's your AC sine wave. You can see.
Those go through 3 wires that put out the third of the power, right? Those diodes.
Nope, those would be different. So if you look, the part that's producing the power is like the stator. The stator's on the outside, it's stationary. That's really producing the power. In the middle, the rotor's spinning, right? But we need a magnetic field in there. So we could either use A, like more of a permanent magnet, and then it's magnetized, or B, in this case, we could actually magnetize them by sending electricity into the electromagnet, and it would only be magnetic when we sent the electricity into the electromagnet. It would do it anytime that, on the older style, that's how it worked. It would do it anytime you turn the key on, it would start to try to send voltage in there through that diode trio, and it would have to do it through that slip ring and the brushes, because remember, the rotor spins, right? So if the rotor's spinning and inside the rotor there's magnets, how are you going to get, you can't put wires on the magnets that are spinning. The wires are going to get ripped off.
That diode right there we just saw.
Uh-huh.
Connected to those 3 places, and that's where the electricity goes through.
I'm going to show you something.
Because it has three, right there, go back.
No, I got to show you something else. Here we go. All right, if you look, see this slip ring? We could send the voltage in here. The slip ring is basically extended out from the rotor. And so if the rotor's spinning, we could actually make a connection to the spinning part by riding a brush on that spinning slip ring. So it's kind of like a commutator. So the slip ring's spinning, 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 but we need to send a voltage into there, so we ride a brush on there, and that voltage will go into the slip ring, into the brush, onto the slip ring, and the slip ring actually gets wired to this magnet. So it's a little more mechanical. That's actually what's up with this one. This one, it's probably hard for you guys to see, but there's a spinning slip ring in here. It's part of the thing that's messed up. That was a failure point. The brushes would fail on that. Right. And so again, it's what they knew back in the day. They've really gone a lot away from this. It would be more simple to put, permanent magnets in there. And then you know what we could do? We can switch the polarity of the field coils out here. See, these stay still. So to me, I would rather do the electrical work on these because they don't spin and just have these be permanent. But back in the day, they were making these electromagnets, and these they'd have to keep switching back and forth. It was just complicated because you never want to magnetize the spinning part with anything other than a permanent magnet if you ask for simplicity. Okay, so there's your rotor that's spinning. Okay, and then we talked a little bit about the fan. Okay, but also the ends of the rotor coil windings are connected to insulated slip rings mounted on the shaft. So those slip rings basically are the point where we can put a brush on it and transfer power into something that's spinning, where otherwise, how would you ever put power to it? That's the whole purpose of the slip ring and the brushes, okay? And then they have to maintain contact at all times so that we can send current to them so that we can magnetize it. Okay, it gets a little bit too detailed maybe, but at least you can kind of understand it. Right, and that's when we were talking about that diode trio. Go ahead, here.
So where did those three on the bottom go to?
These are going to go into the rotor, right? So if we need to magnetize the rotor, or if we need to send voltage to the rotor to magnetize it, we can send voltage into here, and then from here it can split off into three ways, and that'll go onto three different parts of a slip ring with three different brushes and magnetize your spinning rotor magnet.
I just wanted to figure out what that.
Yeah.
Okay.
And again, old school, yeah. This is how we get power into the slip ring in three different ways, and the brushes are going to ride on the slip ring.
That's becoming obsolete.
It's already obsolete. Yeah, exactly, but it's old school. So, however, let's just say that, really the diagnosis stays the same, but let's just say for whatever reason, you absolutely had to rebuild one of them. At least want you to be somewhat familiar. And the other thing is sometimes, the customers want to know a little bit more. So let's just say part of my goal is not just to have you guys be able to diagnose the car, but let's say some of you want to be like management or a foreman or something. Once in a while you get a customer and they're going to say, well, I'm not sure you know what you're doing. Explain to me a little bit more about how that works. And if you know nothing more than this is the alternator and I don't know what's in there or how it works or anything, you might be able to still kind of diagnose the car. But if somebody probes you or asks you, or if you're ever brought into court as allegedly an expert, you need to know just a little bit more than just that's the alternator, and if it's bad, I put one in. You see what I'm saying? So that's a big part of what this is to do. You can understand a little bit more than you need to just to fix it. Cool. So if you remember, the rotor is the spinning part, which means the stator is the still part. And see, this is easier because this doesn't move. And these are the coils that actually generate the power. And these coils are going to be wired into that rectifier bridge. Makes sense? So this is really what we're worried about. But for this to generate the power, the spinning rotor has to have a magnetic field. I'd go with a permanent magnet because then it's always magnet. But in the older cars, the spinning rotor needed to be magnetized, so we'd have to get a current flowing into the spinning rotor, which that's why we needed the slip ring and the brushes, because it was spinning and we needed to send voltage through there. Cool? But this stator out here, this doesn't move. This is much more simple. This is really where the power is generated. Make sense? And this is a whole bunch of coils. So if we were to remember that picture where it showed the 2 field coils, remember those? This is that, except a whole bunch of times over and over. Phase 1, 2, 3, 1, 2, 3, 1, 2, 3. I mean, it's a lot. So we do the same thing, but a whole bunch of times. So that way it's getting, you know, a generator effect. Because if this spinning rotor crosses this stator's magnetic field, it does what we call it cuts the magnetic field. When it cuts the magnetic field, it induces electricity into this. It induces it here, then it induces it here, then here, then here, then here, then here. And then we take all those and combine them, and it gives us a lot of power, but it also gives it a pretty smooth power because there's 3 different phases set off 120 degrees. Make sense? If you only had 1 phase, it could be a lot of power, but it'd be like a lot of power, no power, a lot of power, no power, right? So that's why we set them 120 degrees, made it 3 times, it smooths it out, and then we just have it doing it a whole bunch of times per rotation to make more power. A lot of power. And that's why also on the rotor, you'll notice the rotor has more than 1 magnet if we were to back up. It doesn't just have 1 magnet. This magnet was working on that phase 1, and then it's going into phase 2 and 3, and this one was on another phase 1 and then 2 and 3, and this one's on another phase 1 and then 2 and 3. So you have a whole bunch of magnets on the rotor and a whole bunch of windings on the coil. So it doesn't have to wait to turn 1/3. It's already onto the next one, the next one, the next one, the next one, because there's so many. So if you watch the animation video, I think you'll really love it. But I've thought of so many different ways where I could try to explain it better, and I can't even come close to the animation. Not even close. When you see the animation, a lot of what I said will clear. All right, so now when we talk about the stator, that's where the real power comes from. We can wire it as a Y. You know how Y is spelled? In this case, W-Y-E. Or we could do a delta. Honestly, not really a huge deal, but mainly it's just how they look. Does that left one look like a Y? Yeah. And this one look like a delta, right? So whatever, it's not a real big deal. They're going to connect to the field windings. And then basically they're going to go to the output. Output, output, output. Or output, output, output. Just a different design. So if you ever hear, oh, it's like you're reading some manual and it says it's a Y wound alternator, and you're like, okay, cool. You know, if Tim was here, we could say, Tim, why do the electrical engineers pick the Y versus the delta? I'm sure there's some reason, but I don't even really try to pursue that. I can at least carry a conversation. This is a Y wound and this is a delta wound, and really they don't do all that much from the technician perspective. Cool. All right. Now we'll get into a little bit more of what you need to really know. When we go to work on these, if you're in the service manual, a lot of times it'll give you a diagram like this. So is this a Y or a delta?
Delta.
No, the delta was like a triangle. This is, well, it's a Y, but it's kind of upside down, huh? It would, yeah. If you looked at it like upside, it's like an upside down Y, but that's a Y. All right. So if you were to try to do charging system diagnosis, this is where the technician spends their time, right? Exactly the Y or the delta or, you know, those details and the slip ring, and that's engineering stuff. This would be like, I got a car that doesn't charge, the battery light is on. How do I determine if it's an alternator or not? Okay, so let's take a quick look at this. And right here, you notice they're actually calling it the generator. And in the video, I list the differences. If you use this, you could commutate the generator and make it so it always puts out DC. But a lot of times what we'll do is we'll actually just let it put out AC and then we'll rectify it into DC. So that gets into the details, minutia, if you will, of generator, alternator. Typically, in automotive, we'll kind of interchange them. In reality, I'm going to bet you, it's generating AC, right? You can tell when you have the stator winding that looks like this. This is 3-phase AC. You agree? That's an alternator. Then it goes into the rectifier bridge, which makes it into DC. Now, does that make it into a generator or an alternator? Whatever, who cares? Technically, it's an alternator that is rectified into DC, but they may call it a generator, and the reason why is because if they were to take an AC part like this and not run it through a rectifier, they could actually have these go to a commutator and have it actually put out DC right here. They don't have to rectify it. That would technically be a generator. But it's kind of weird, so whatever, who cares? It's going to basically do all this stuff inside this box within the alternator or generator. Okay? So we can't come in here. You want to test this diode right here? You want to put your meter right there? You can't do that. That's inside. You can't. You know what you can do? You can test B, M, S, I, G, L, and that's it. So let me tell you what B is. Can you get an idea of what B is?
Rotary?
True. So what's that look like? That's the big boy. Remember the big wire that goes to an alternator right here? This big cable? That's the big 6 gauge or 4 gauge or so, or 8, whatever. That's the big one. All right? If you were to take your meter and you were to put it right here and you were to get 0 volts, what do you think? Okay, then we could go to the battery and let's say the battery has 12.6.
Oh, fuse.
Oh, and look, so you'd have to actually see, are you getting 12 volts here? Let's say you get 12 volts here, yes, but here you get 0. It'd be that fuse. Let's say you get 12 here, 12 here, 12 here, 0 here, 12 here. The 120 amp alternator fuse, right? So there's a lot of times a main fuse, but this may be a fusible link, like a big wire, but that has a gummy fusible link section, remember that? And that basically powers everything. Then right here, we have a 120 amp alternator fuse. That's for the big positive cable. I've seen some people jump start the car backwards and actually blow that fuse. I've also seen people try to change an alternator without disconnecting the battery, and they take this off and they accidentally ground it to the case right here, and that could potentially blow that fuse. You know that would cause a no charge, right? You'd be like, oh, it needs an alternator again. You better make sure that that fuse is good. Do not replace a $300 alternator because of a $4 fuse. Make sense? This is why you want the diagram. So right off the bat, you guys can determine B should have 12 point whatever the battery had. Source voltage, we'll call it. Whatever source voltage was, it should have it here. Make sense so far? All right, now let's take a look at M. What do you think M is? True, but what were we talking about before? What does the ECM do?
Signals.
Okay, the signals. Now hold up. Here we're using our meter to check voltage. If you want to check this signal, any idea how we go about that? How could we? It wouldn't be the scan tool. This is close. Oscilloscope. It was there. You had it. Okay, remember how I drew that signal? Technically, if you went with your meter, it would be hard to really read what's going on there. You know, the meter would be like, voltage, no voltage, voltage, no voltage. The meter has a hard time saying, there's voltage 10% of the time on and 90% of the time off. This is actually better for an oscilloscope. Make sense? There are good meters, like a nice fluke meter, where you can put it on duty cycle and you can put your meter there and it will give you a number on screen that would say 10. If it says 10% duty cycle, that means it's getting 10% on time, but a lot of meters won't do duty cycle. So at this point, if you really want to be able to diagnose this, you got to get into the oscilloscope, and the oscilloscope is going to graph it. Make sense?
Is there any multimeters that have both?
There are graphing multimeters, and like a nice meter can do the duty cycle or pulse width right out of the right out the box. They're nice, yes.
But it's like
Not cheap.
It has a multimeter and a...
Not exactly an oscilloscope, but like, this is my thing. As a technician, not an engineer, I don't really care to do a science experiment on the car. I'm going to be really blunt with you. My goal is to diagnose it as quick as possible with as least effort as possible. But it's got to be correct. All right. So if I put no effort and I'm wrong, I'm liable to be sued and have to give a refund. Plus, to be really honest and in character, if I misdiagnose a vehicle, I feel horrible. I end up giving the job away anyway. So I need to be right. I can't be wrong again. And I've been wrong plenty of times, right? So I want to diagnose this, but what I'm not looking to do is get out my oscilloscope and my test leads and my thing and record and like do a whole big old thing, right? Because if I spend 3 hours diagnosing this and I go to the customer and I say, yep, I'm going to bill you 3 hours to diagnose that. See, at my level, with the investments I've made and the education, the training, I'm not billing $20, $30 an hour. You know, if I'm going to go to the customer and be talking 50, 75, you know, if it's really complex, let's say that I'm representing more of a shop. If the shop's billing 150 an hour, I could probably do it for 100. You know, I could definitely do it for 100, but like, I can't go to them and be like, hey, I spent 3 hours diagnosing your no charge. You owe me $300 for the diagnosis. And be like, what? See what I'm saying? I just want to get down and dirty and diagnose it quick. So rather than do the oscilloscope for me, because it takes more time, I got to load up the computer, I got to plug it in, I got to start up the program. I would like to get a meter that will just give me a percentage right then and there, boom, done. And my diagnosis is quick. All I need to know is it getting, sorry, I'm M, is it getting the correct signal? That's all I need to know. Make sense? So if a meter does it for me, cool. But generally, the more by the book is the oscilloscope. I'd put the oscilloscope on and it would pull up a screen. Do you remember that thing I drew? If it was 10%, it should be up 10, down 90. Up 10, down 90. If it shows that on screen, I know it's getting what it's supposed to get right there. Let's just say I put it up on screen and it shows a flat line 0. Not getting it, but then I got to think, is it the wire or is it the module? And the answer is, it could be, but maybe not. The next test would be if I put the thing here and I get a flat line, and then I probe up here and I get the 10 and the 90 and the... Right, so we'd have to probe here and here. It's not that different than available voltage. Let's just pretend it was supposed to get 12 volts here. If it didn't get 12, I'd go here. If it got 12 here, but it lost it here, there would be the wire, right? It's real similar with the oscilloscope. If it's got a bad signal here, but it's got a good signal here, it lost it in the wire. Then I'm looking for a broken wire, a loose terminal. Very similar to a voltage drop, except you're using oscilloscope signal. Does it have a signal? No. Does it have a signal? Yes. Well, then the ECM is good and the wire is bad. Now, if the ECM is not putting out any signal, then I might have to get a little more, maybe get the scan tool, check to see if it has codes, see if I can command it to 100% and see any sort of change, right? But this is a big part of our diagnosis right here. I'm going to say 75% of techs, they run out of gas right here and they're just like, well, I checked for voltage here and I checked for voltage here. And, you know, in this one, it actually has voltage right here, but they don't want to bust out the oscilloscope and they don't know how to really check for the pulse width modulation if they even have the right meter. Make sense? I want you to be able to handle that. Okay? Then from there, yes, you'll notice it gets something on S and something on IG. S would come straight from the battery. So that's the S terminal. And then IG is actually coming from 10 amp gauge number 1. This, I'm pretty sure, only gets voltage when you turn the key on. I'm really confident. And then down here, the ground comes from the case, but this ground actually comes, oh, that's actually not a ground. Okay, I know what this is. Pause. B, M, S, and IG determine whether or not this alternator will work. If you're missing B, M, S, or IG, this alternator is not going to work, and a new alternator is not going to fix it. So when we are trying to diagnose the charging system, basically, we know it's into the alternator. The question is the alternator getting what it needs? It needs 12 volts here. It needs this pulse width modulated signal here. It needs 12 volts here, and it needs 12 volts when the ignition's on. That's why it's IG. Okay? If it has those 4, and the alternator is not charging, it's the alternator. Make sense? If it doesn't have one of these, we got to figure out why. Diagnose the circuit. Fuse, module, wire, fuse, whatever. Diagnose those. Cool? Now what's happening down here is different. The L terminal goes to the charge indicator in the combination meter. You know what that means? Your instrument panel. This is the battery light right here. That's the battery light. The reason it does it is because, look, if you have, let's say, 12 volts coming out of your gauge and it goes to this, and this is grounded because the alternator is not charging, this would have 12 volts and ground. See the pink and the green? If this has 12 volts and ground, what's this LED going to do? It's an LED now. Light up. Yeah, it's going to light up. This is the battery light on. It should be, because it's if it's got 12 volts in ground, that's going to mean the light bulb will light. So picture a light bulb. In this case, it's an LED, but it's similar to a light bulb. Now, what happens when you start the car and the alternator starts charging? This voltage regulator, integrated circuit regulator, is going to put out, I don't know, 13.5 volts. If we have 13.5 volts on this green wire, and you have 13.5 volts coming in and 13.5 volts coming in on the ground side, what happens to this light? Bingo. So if your alternator charges, voltage is met with voltage, there's no difference in voltage, the charge lights off. If your alternator doesn't charge, voltage gets grounded because it's not generating voltage and the light is on. Make sense? So the alternator triggers this light. This light should only be on if the alternator is not charging. You turn the key on, but don't start the engine. Does the alternator generate? Yeah. No. When you just turn the key on, it's not turning yet, right? It's not turning. So this would be ground. This would be positive. Your battery light's on. And it should be. When does it go off? Exactly. You're going to fire it up. This is going to turn on, or two things. If you turn the key off, yeah, it'll go off because it cuts the power. But if you start the car, this should generate, and this light should go off because there's no 12 volts in ground. There's 12 volts and 12 volts. Or in the running case, 13 point something and 13 point something. There's no ability for this to come on because it lost its ground. In another way to explain it, if this isn't charging, this wire is grounded, the light's on. Once you start it, this should no longer be grounded, the light should go off, but if it's not working, it's still grounded and the light's still on, and then you're troubleshooting. Kind of see how the warning light comes on now a little bit? You guys have seen the old cars where it shows the actual voltage needle? Those are nice. When you shut it off and you're hanging out the drive-in with your BFF talking about the movie or whatever, you can have your voltage start at 12.6 and you can watch that gauge slowly go down as your battery's dying. When you start it up, it should, yeah, you should remember those. You could start it up and the voltage should jump back up, right? But people were watching that too much and thinking that was a gauge on how full their battery was or something. So they mostly eliminated that and they just went to a dummy light, you may say. Cool. Oh yeah. All right, so that was the main way that the troubleshooting occurs. Let's just say, like, remember I told you that guy were behind and his lights were going dim, dim, dim. Remember how I told you he forgot to plug something in? Well, if this was disconnected, this won't charge. The light will be on. Make sense? So he just had to connect. Sometimes it varies, right? But there's always one big wire, and that's the battery terminal. Then sometimes there's one wire, two wires, three wires, or four wires. There's another small connector. In this case, it's the ECM signal, the battery signal, the ignition signal, and the L terminal, which controls the light, right? So we have a small connector with little wires. Small, 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 small wire.
So
that's the small one. This one is 4 small wires and 1 big wire. Yeah, so they may call this a 4-wire. Sometimes they don't count the big one. Sometimes they do. Yeah, that's the plug right there. Bingo. This one is the one you got to actually undo the nut, and it's got the terminal, and it's covered up by the little rubber boot. Yeah, this is fairly common. The guy whose battery died on the way to that trip, he forgot to plug in this connector, so it was missing all these, and it was just dying as he was driving. You know, I was thinking about it like, Ken, wasn't your battery light on? And he was kind of spazzy. He probably wasn't paying attention. So there was a clue there. He didn't have to wait till it was dying. He could have just checked it, right? All right, so then we talk about some of the more mechanical things. You guys can see they vary, right? Different types of end frames. These ones are more vented. This is less vented. This one's actually liquid cooled. So this is air cooled. This is cooled by coolant or water. They vary, but they're very similar. This is what I was looking for earlier. Remember we were talking about how we had to magnetize these? Well, this is how we'd actually get the voltage in. This wire would go to a brush. This brush would ride on the slip ring. The slip ring spins. The slip ring is actually connected to the shaft, and the shaft is connected to the wire, right? So, yeah, that's just an old school slip ring and brushes. Cool. And you can see the slip ring and brushes on the back of this one. And then you can see different types of rectifier. So this was a nice diagram, mainly because you can kind of see how it all lays out. The battery sends the 12 volts in, which is connected through the slip rings and brushes, which is going to end up going through the regulator into the field coil. And we got the diode rectifier bridge, and this is a delta style, delta wound alternator, right? So they vary. There's your rectifier. Here's the fan in red. Here's an overrunning clutch. So this one's going to get a little extra attention. When we're running the vehicle, right, you're running it, the alternator puts, a magnetic field, and it's going to resist the motion, right? But the engine's running. Now, when we turn the engine off, sometimes what tends to happen is the alternator might tend to keep trying to spin, or sometimes when you turn the engine off, what'll happen, let's say you have a piston that's coming up on compression stroke, you turn the engine off, the piston might actually push back down because it doesn't really want to be in compression. It'll turn the engine backwards. When it does that, it tries to turn the alternator backwards, and it doesn't really like that. So what we'll do is we'll put an overrunning clutch on. What an overrunning clutch will do is when the alternator is being driven the right direction, it'll lock up. But when the engine tries to turn in reverse, when you shut the engine off, it'll actually freewheel, which means it won't make the alternator spin the wrong way because they don't really like that. Make sense? So this part right here, you shut the engine off, it'll just basically slip backwards, the pulley itself. Locked, and then if you were to turn it this way, it would slip. This, I was looking for one. This doesn't have an overrunning clutch. I didn't have one. This is old school. But an overrunning clutch can be on the new school. One of the reasons that one's critical is if you have a bad overrunning clutch, they can make noise. They could actually freewheel. You could be seeing this pulley spin, but it actually won't turn the shaft. But the main thing is probably noise. They do tend to, when they start to fail, they start making noise and clunking and bumping. Technically, to fix it, you could change the overrunning clutch and pulley, but a lot of times we're ended up doing the whole alternator too. Right, so it's going to help with belt wear, smoothness, quietness, increase alternator lifespan. All right, now let's say we're ready to diagnose. Okay, now you guys understand the whole system. Here you go. Customer calls, their battery lights on, or customer says, Pablo, are you changing my Alternator? And I say, yeah, cambio, sí. And then you say, all right, here's how I'm going to start. I'm just telling you these conversations. I could play them in my mind. All right, I'm going to start by, what do you think? Visual inspection. If you go all crazy and you bust out that oscilloscope and you start trying to check pulse width modulation and duty cycle and all that type of stuff, and you don't realize this is disconnected or this is disconnected or this is ripped out or a mouse chewed right there, shame on you. So let's just start with a visual, right? Visual, what's up with the battery? What's up with the fuses? How is the belt? If the belt's ripped off, is it going to charge? No. Do you need the oscilloscope to be able to test that? No, you need to look. Look at the belt. Overall, look and make sure the wiring is plugged into the alternator and maybe related around there. Check for noise, check for the charging indicator. If you do this, you should have a pretty good idea of what you got. Make sense? Is it a guarantee? No, but you're going to catch probably 7 out of 10 faults just with your visual. Just with your visual. If your visual is good, because basically, remember what we're doing. If it's a charging system issue, we think it's probably the alternator, huh? It probably is. But we have to eliminate other possibilities, because if we change the alternator and come to find out the belt was off of it, you're fired. If we change the alternator, come to find out the fuse was blown, you're fired. If we go to change the alternator, come to find out the battery was extremely sulfated, so bad it wouldn't charge, you're fired. You're getting fired a lot today. If we find out that one of the wires was chewed or disconnected, and we change the alternator and we bill the customer, you're fired, right? So start with the visual. You'll catch a lot of the stuff.
Well, if it's a fuse, you have to figure out why the fuse blew.
Of course, we're detectives, so I'll give you a couple different scenarios that I've seen. At my other school, we have a collision department. You know what they do? Fix dents and paint stuff and whatever. And actually, you probably love this class, so I don't want to get you too excited, but they started a class called RAP. You know what they do in RAP class? Wiki. No, yeah, not wrapping burritos. They're doing wraps. Yeah, they're wrapping the cars. So it is pretty cool. They'll pull a car in and like they're not designing the wraps. They're simply just pulling the wrap off the machine, put it on, squeegeeing the bubbles out. It's really cool. But the thing is, there is. But their skill set's very different than ours. So they're over there doing the wrap, and one of the hardest ones to wrap is like a 2022 Tundra, and we have one. So they asked, I'm like, yeah, we'll share the Tundra. It'll be fine. Use it for wrap. When I need it for four-wheel drive and stuff, I'm going to come get it though, okay? So we're good. Now, you know, I'm going to put this really nicely. People who are doing collision are a little more artists, right? They're looking at the wrap. They're making sure there's no bubbles. They have amazing talent with color. They have a whole class called color matching. How to make the color more red, more blue, more metallic, more like it's artist stuff, right? Trying to explain them about how to not have a battery die though, not necessarily their strong point, right? So I let them borrow the Tundra. Next thing you know, the battery's dead. The battery's dead today, tomorrow, the next day for the next 3 months. What's the status of a dead battery after 3 months? It ain't coming back, okay? So that battery's shot. That battery's like $180, and we're like, you know, nah, just don't even put 180 into it. They're just going to kill it again because they pull the car in, right? And they got doors open. And in their defense, you got to open the door to do the wrap, right? But the right thing to do would be put it on the battery charger to keep the battery up. But they'll just pull it in, open the doors, the dome lights are on, the battery's dead. When they're done with it, bang, jump it, pull it out. Park it, it's dead. Not leave it run enough to charge the battery, it's dead. Then tomorrow, jump it, drive it in. Then jump it, drive it out. Jump it, drive it in. Well, one of the students did the old jumperoo, a little old jumperoo backwards. Okay, makes sense? So then we go to start the car and it's like, well, it won't jump. And then we found it blew the main fuse for the battery and we did that. And then after that, it would jump and start, but the alternator wouldn't charge. The battery light was on. And so looking a little further, it blew the main alternator fuse that was like 125 amps or something. So yes, if that fuse is blown, trust me, there's a reason that blew. But it might be, however, as simple as they jumped it backwards. So with that one, I asked some questions like, hey, who jumped the car yesterday? Oh, I don't know, somebody over there and somebody over here and somebody over there and whatever. I finally got a hold of the kid. I knew who the kid was. And I was like, hey, anything happened weird? And he's like, well, I think, and I said, listen, you telling me the truth is going to help me understand if I need to look at something else. So just tell me how it is. He says, yeah, I think I had it backwards because there was a lot of sparking and smoking, and then I corrected it. I was like, okay, cool. That explains the blown fuse. That's it. You just got to figure out why. Now, if that fuse had blown and you don't think anybody had worked on it, I might be real worried about a wire that's chafed right here. If that wire is the big positive and it touches the alternator, you know that'll be a short circuit. It'll blow the fuse, right? So if the fuse is blown, absolutely, we got to figure out why did the fuse blow. Make sense? So when we're looking at this, you know, a lot of times we're trying to get a whole picture of what's the deal with the failure. If it's a fuse blown, why did it blow? Did somebody work on it? A lot of times the first thing I'll do is look to see if anybody else worked on it. You know, two-legged varmints, right? The two-legged varmints got in there and done it. You know, the human ones. They messed it up, possibly, quite possibly. Cool. So we could look at some stuff. We could listen. Sometimes the diodes will actually make noise. Sometimes there's physical damage. Sometimes the belt will make noise. Sometimes the bearing will make noise. This is not real technical. The other thing is, of course, we got to inspect the battery. But how would you really tell if the battery is good or bad? Yeah, probably going to go right for the battery tester. If the battery tester shows that it's sulfated, you know, I would say like, well, let me weigh this. First off, I got to tell the customer, hey, your battery's bad for sure. But it still could be more than the battery, because see, that's where it's tricky. An alternator not charging will leave a battery dead, and a battery staying dead will kill a battery, but a really dead battery can make an alternator act kind of funny, you know. So this one's where it's a little bit of a catch-22. But if it's really a charging system concern, I'd focus more on the alternator side of things than the battery, but just make sure you're communicating well with the customer or whatever, that, hey, if your battery is really messed up, like I had one where the battery was totally dead and it wouldn't charge, and I used the jump pack, like the lithium ion smart jumper, no code, nice one, and with it jumped, the alternator wouldn't charge. And it was sort of like, I think it's the alternator, but I can't say your battery is so dead. Why don't we start with the battery just to simplify it? And the new battery totally fixed it. Done. That computer wouldn't charge my smart jump pack for whatever various reason. It was a little hard to say. But generally, you know, like corrosion and stuff like that, that's something that we'd be concerned about. But I wouldn't say like, wait a minute, we need to replace the battery. We need to do this. We need to do that before we diagnose. That would be pretty rare. You should be able to diagnose it without giving the battery too much attention. What do you think, Mason? You like it?
Or it could be like a loose terminal.
If your terminal's loose right here, it can cause some issues with the charging system, sure. So you might have to do, you know, give it a little bit of attention at the battery, because the battery does have an effect on the alternator. But just understand what I'm saying. Too many people on the forums, you say like, oh, my car's not charging, and they're just obsessed with doing battery maintenance. They're just like, got to do the terminals and clean this and clean that. And they'll do all sorts of battery maintenance, but like at the end of the day, we also want to get on to checking the charging system. Kind of makes sense. So give it a little attention, but don't run out of gas on just the battery. Cool. And then like we've talked about for this whole class, normally we're going to replace the entire alternator with a newer rebuilt. Makes sense. That's what we do. If we have faulty bearings, replace it with a rebuilt. If it's got a high-pitched whine or a low-pitched growl, it could be alternator fielding normally, or it could be bearing. But then the thing is, like, if you think it's a bearing, one of the best things that we could do, stethoscope, or even like if you don't have a stethoscope, a screwdriver, put it here and listen. If it's quiet over here and it's quiet over there, and then here you hear, you know, that's kind of how you'd know. Just helping identify the noise. Don't diagnose it like this, like, your ear can't really pinpoint here. There's a lot of noises that'll catch your ear. Use a stethoscope or at least a screwdriver to really nail that one down. Okay. And that's kind of what we're showing here. And the other thing is, if you absolutely want to be sure if it's the alternator, you could take the belt off of it. And if you run the engine and the noise is still there, but the belt is off, it ain't the alternator. The alternator's not spinning, right? So you can be as thorough as you need to be right there. Also, that stethoscope is like $10. You should get one, right? If you go to look at the fuses, just keep in mind, the fuse could look like this, Alt 120, that's a big one. Sometimes those fuses are like full bolt-in assemblies like this. So if you need to change that fuse, it's not as simple as you just go and get one out of your little junk bin. You're gonna probably have to order one of these. This is gonna be a big fuse. A maxi fuse or a combined fuse like this, so don't take it lightly. The bummer with these is it's real hard to see the fuse, and there's actually no spot to test it. So the maxi fuse is nicer because you can measure voltage in and voltage out if it has the maxi style fuse. They just vary, okay? They can look very different. Checking the belt. All right, so if a vehicle has a no charge condition and the belt has cracks in it, what are your thoughts?
It's no good.
The belt's no good, but how do you want to proceed on this? And I'm okay with this discussion. Let's be real about it. I have how I would proceed, but I want to know how you'd proceed.
Replace it just in case.
All right, so if they were to be like, hey, I'm towing my car in, the battery was dead, I jumped it, and as soon as I, pulled the jumper off, it died. Will you diagnose it? You could be like, hey, your belt's cracked, but I'm going to tell you, dealing with customers a lot, you know what they're going to say? Oh, it's just my belt? That's going to fix it? You think the belt's going to fix it? No. You think these little cracks are going to cause it not to charge? No. So I want to make sure I put this clearly into context. When you're looking at the alternator, you got to understand, does your symptom match the condition? If you're having a noise, this would match a noise. If you're having a complete no charge condition, the car was towed in, little cracks on the belt don't really match it. So I'd more be like, all right, I saw that, let me note it, because I'm going to tell the customer, hey, you should do that belt as a maintenance, and I'll get back to why. But then I would probably, take a look at the alignment, take a look at the belt tension, whatever. And if it's all reasonable, I'm going to proceed with diagnosing the actual charging system. Makes sense? Like checking with my meter, checking voltages, seeing if the alternator is good or bad. Cool. But if I diagnose it as a bad alternator and I'm going to replace this alternator, what should I also be replacing? Right. So when I call, I'm not going to say, hey, let's start with the belt. I'm going to like say, okay, I recognize the belt needs to be addressed, but I'm going to also do the diagnosis. I'm going to say, here's your actual problem. Your alternator caused the battery to die. Your alternator's not charging. The alternator replacement's going to be $500. But also, when I do the alternator, I have to take the belt off. I'm going to recommend you buy a belt. The belt's only $30. I won't charge you any extra labor, and you really need to take care of that. And if they say, well, why do I need the belt if the alternator's the problem? What would your answer be? This belt could fail any day. I mean, this belt will leave you just as stranded as an alternator. So if you don't want to do the belt, no problem. I'll put your old piece of junk belt off, but you're going to sign a waiver saying if the belt flies off and it no longer charges and whatever, there's nothing going to be covered as like a warranty type of a comeback condition. Make sense? Say like, hey, you should have done the belt while it was there. Make sense? So same with the battery terminals, if they're a little corroded and stuff. I'm more than good to do the repair and also do the maintenance that's going to keep it from coming back. But I would really caution you against telling them, well, we need to suck all the maintenance off this car. We're going to clean the battery terminals. We're going to do the belt. We're going to also polish your headlights. We're going to do an alignment. And then after that, we'll think about diagnosing the reason that you towed the car in. See what I'm saying? Like, don't be like that now. And just kind of understand, be aware of the situation. Now, here we go. You want to check the alternator? This is how simple it is. Measure the battery voltage and charging current at 2,000 RPM. Sorry for the overlap there. I'm using my other computer, so it's using a different program than usual. Okay, so what do we need to do that?
Check fire voltage.
But what's it saying about the RPM?
So you have to rev it.
Oh, so we got to kind of have like two people. Yeah, so if you're trying to do this with the meter, you need a Tony. Hey, Tony, can you rev it up to 2,000? And Tony's like, 20,000? Ring, bang, 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 boom, bang, pow. Bing, bang, bing, bing, bang, bang. No, like 2,000, Tony, just like a little above idle, you know. 2,000's like this. Not, it makes sense? So 2,000, give me 2,000. You're going to check the voltage. What are we getting on that measurement? 14, I mean, that's fine. What if you were getting 12.6?
Still fine. So good.
What's good about that now? 12.6 is a fully charged battery. This vehicle is running at 2,000 RPM. Oh, heck no. All right, so think about this.
14 and then it's at 12.
All right, I'm gonna put it in reverse, Terry. Engine off, 12.6 is amazing. That's a charged battery. Engine on, you start the engine, it better be a lot higher than that. It better be 13 something at least. At 2,000 RPMs, yeah, it should be well into 13, probably more like 14, sometimes even above 14.
12 would be like as if the battery was dead, right?
12 would be like if the alternator wasn't charging. You're running only off the battery, right? So ideally, I'd change this test slightly. I'd get the battery, I'd check the voltage, okay? Let's say it's 12.6. When I start the engine, it's probably going to dip because it pulls a bunch of current out, right? But then once the engine's running, what should it be reading? Definitely not 12.6, makes sense? It should be something like this, 13 something, even 13.2, whatever, but never the same as when it wasn't running. If your voltage is the same whether it's running or not running, your alternator's bingo right there. It's not charging if it's the same off as on. If it's running, it needs to be a lot more than when it was not running, or that alternator's not working, right? So that's your first basic test. That's the test I described in the beginning. Now you understand why, kind of, right? Soon as you go to start it, that alternator's spinning, right? The rotor is spinning, the stator is still, the magnetic fields, if you don't understand the Y and the delta, that's fine. But you need to understand this all the way. Battery voltage, 12.6. Start it, not 12.6 anymore. If it's still 12.6, the alternator's not doing nothing. Then you could do it janky style. You could pull the battery terminal off, and if it dies, alternator, but if it still runs, the alternator is good, okay? That's a little janky style. So we're gonna do it like a little bit more by the book, right? When it's running, let's say you get 14 volts. The next thing is, we need to know how many amps are coming out of the alternator, right? Because remember, that's why we went into how it has the 3 phases and the different diodes and all that type of stuff. Just seeing that it goes from 12.6 to 14, that tells you it's charging, but how do we know one of those 3 phases isn't bad? Make sense? You got to test the actual output of the alternator. You need to do that with an amp clamp. So remember how we were measuring a little bit with this when we checked the starter? This is going to measure the amount of amperage that is leaving like this, because the alternator generates it and it goes into the battery. So we orientate this where it's measuring this way, and then we're going to see how many amps. And this actually is not correct, but if we were to look at this, we should have, well, it depends. This is showing no load. You know what that means? No headlights, not running the mirrors, not running the windows. It shouldn't put much more than 10 amps out, because this shows a different number because it's using an amp clamp on the meter. If this was just an amp clamp, it might say like 8 amps, 9 amps. That'd be pretty low. Why is it so low though? Because it's good, but it's low. Why is it low? There's no load. Make sense? We're not loading it up. We're not putting a whole bunch of loads on there. What if you were running electric power steering and windows and lights and wipers and stuff? Then that number should be much higher, right? And that's what we get into on the next one. Okay, with a load, 30 amps would be like, hey, it was 10 amps with no load. Then when we put a bunch of electronic stuff on, the amperage increases. Is the alternator responding and putting out more? It is, so that's kind of telling you like, hey, this alternator is working. It has at least the ability to put out 30 amps. Make sense? But if this alternator is rated for 100 amps, we got to test it in a different way if you want to know if it makes all 100 amps. And that's when we'd have to get like a load tester. Make sense? And sometimes we'll go that far and sometimes we won't. But it's more than just check the voltage if you want the extensive test. If you want your quick test to tell whether the charging system's charging at all or not, just this will tell you. Make sense? If it's, let's say it's 12.2 and you start the car and it's 12.2. What do you determine?
Something ain't right. If it ain't 12,
Something ain't right for sure. But if the battery was 12.2, it doesn't tell us for sure the battery's bad, but the battery was discharged. But there's a bigger and much more serious issue. I started the car and it's still at 12.2. Yeah, so it's not charging, right? So that's the down and dirty, whether the charging system's working at all or not. And honestly, most of the time, if an alternator fails, it doesn't charge at all. Once in a great while, it can charge at 30 amps, but it can't make it past 60 because it's got, let's say, one of the phases is bad and it can only do a max of 60, but once in a while you need 90, right? Once in a while, but a lot of times they'll fail in such a way where they won't charge at all. It would have failed this test. This test is a little bit more advanced, and it tests it more thoroughly though. Now, if you wanted to do voltage drop tests of like, let's say the terminals and the wires, right? If you look at your alternator, you know that it needs this connection right here. What if your connection right here is corroded and loose and messed up? That's going to have an effect, right? How are you going to measure it though? Well, here you go. Here's your positive lead. We put it right on that terminal. That's the big battery terminal. Here's your negative lead. We put it on the red terminal of the battery. That's going to test how much voltage is dropping. Because remember, when it's running, this is the source of the power. Right there. Yeah, the battery has power, but really, your alternator is the thing putting out 14 volts. Okay? If your battery is 12.6 normally, but your alternator is putting out 14, the current flow is actually going this way. That's kind of crazy, huh? It is. So you put it on the most positive, which is the alternator B terminal. Put your red lead there, put your black lead there. How many volts are dropping across that wire? Can you see that number? How much? 0.1, that's great. Guess what? That terminal's good, this wire's good, this fuse is good, all these connections are good. You don't have an issue with that big positive terminal. Make sense? We just voltage drop that terminal. Now let's just say you wanted to check the ground. You'd actually go from the alternator case. So it'd be like the housing right here. And then that would be your positive. And then your negative would be at your most negative, which would be at the battery terminal. And then you're not checking a cable though. You're checking this thing connection and ground to the bracket, to the engine block, through the engine block, through the ground cable that goes to the frame, and the chassis ground that goes to the battery, right? So this is checking like the whole chassis ground right here. And in this case, you're getting, shoot, that's really good. Not even a 0.1, you're getting like a 0.05. That's like half of a 0.1. That's a great reading. So you know that your grounding of your alternator to the bracket and to the block are good. You know your voltage drop on the big terminal is good, on the big battery cable. That's good. And so we're still progressing, right? That's how you'd check the big high current stuff. The way that, if you'll recall, the way we would check this one is the oscilloscope, or a good meter that can give us the duty cycle and pulse width, right? This one should have how much? Look at the diagram. It depends on the source. So if we are key on, engine off, what do you expect the source might be? 12-ish, 12.6, 12.2, whatever. So it should have about 12 point something here. But what if it's running? What should be here?
13 point something.
Yeah, it depends. Yeah, 13 something, maybe 14, maybe 13.7. I don't know. Whatever the source is. So we got to know our source. If you check if it's running and you check the battery and the battery says 13.6, then you should have 13.6 here. And what should you have here? 13.6. See, it's easy to get stuck on like 12 volts. 12 volts was true when the engine wasn't running. Cool? When the engine's running, that changes the numbers. The engine running makes it so the alternator's putting out some amount of voltage at the B terminal. That sets the voltage for the whole system, because this goes straight to the battery. Now the whole system's running way above 12 something. The whole system's running at whatever this puts out. 13.6, 14.0. You know, see what I'm saying? Kind of depends. Depends on the car. Especially the old cars, they would tend to run high. Cool, so we can do those voltage drop tests. Then if you wanted to check that pulley, make sure it locks one way, make sure it free spins the other way. Now here's a new concept. Hybrids, something you guys love. Anybody driving their Prius today? All right, they don't have alternators. You heard me. They don't have this. They don't need this. They don't want this. You want to know why? True, but think about it. That big battery is for more like the hybrid functions. It still needs a little 12-volt battery to run like the radio, to run some of the 12-volt items. In fact, mainly in a hybrid, the main purpose of the 12-volt battery is to give power to close contactors to unleash the big power of the big battery. But we still need one of these. We still need a 12-volt system. So here's how it does it. It's going to use one or more high-powered electric motors to start the engine. So this battery's small, remember? Cool. And then it's going to provide power to assist the internal combustion engine. And then when it comes to a stop, the ICE will shut off. So wait a minute. How is it really talking about how it charges? It doesn't really say a whole lot about how it charges there. It just gives you a little bit of overall on how the hybrid works, which you should be familiar with. Then look, a DC to DC converter. All right, DC to DC. We don't have AC. We don't need AC. We don't want AC. You got a big DC high voltage battery that runs, let's just call it at 240 volts. That 240 volts is way too much to charge this battery though, isn't it? You're going to try to put 240 into here, this thing's going to explode in your face. Boom. So what we could do, we'll take a converter. We'll take our 240 volts DC, we'll step it down to 13.6, 14 volts. And then we'll charge this battery using the DC-DC converter. Make sense? There's no reason to have a spinning alternator. We have a big MG, motor generator, charges the big battery. We just take a little bit of power from the big battery, drop it down to 14 volts or so, and then have it charge this little battery. If you had a hybrid that had a dead 12-volt battery, you could actually put your meter on here, measure the 12 volts, start the engine, and it should jump up to 14 or 13.6 or 13 something. That would tell you the DC to DC converter is working. Make sense? Go ahead. Same thing as when the alternator fails. If you put your meter here and this thing reads 12.2 volts and you turn the car on in a hybrid, that doesn't necessarily mean the engine starts, right? But if you power a hybrid up and the ready light comes on and everything's alive, ready to drive, this should definitely jump up to the 13.6 or 14 something. If it doesn't, investigate the wiring from the DC to DC converter to this. So the DC-DC converter sends out wire on that cable. It goes through a fuse. We got to voltage drop the cable. We check the fuse. But ultimately, if you were to test right at the DC to DC converter and it were to not make your 13.6, the DC-DC converter's bad. You can replace it. But it doesn't have a belt. It's just like a box. And a lot of times it's a box that's part of the big inverter, which is $4,000. So, but they're pretty reliable actually. They're much more reliable than alternator. They just don't have moving parts. There's no slip ring and brushes. There's no diodes to fail. It's like, actually there probably is diodes in it, but there's no slip ring and brushes. So it's kind of better, maybe. Kind of makes sense. Pretty simple. Won't go crazy on that one. There's your DC-DC. Talks about how it takes 13.5 to 5 point volts, which it makes from a big, much higher voltage. It's really actually pretty similar to the alternator as far as testing goes. They can produce maybe 45 to 50 amps. They don't have to really make that much because the hybrid doesn't rely on the 12 volt system as much as the regular gas car. This is the DC to DC converter. Actually, the DC to DC converter is part of this overall larger hybrid inverter. I was looking at that. Yeah, actually it looks like, I think they actually split the DC-DC converter off. That looks a little overly complex for a DC-DC converter, but I think it is. But a hybrid inverter looks pretty similar, but you're gonna see a lot more orange cables. So you may have these two cables coming from the big high voltage battery, these cables coming and going from MG1, these cables coming and going from MG2, and then somewhere in here there will be a DC-DC converter and just regular battery cables going over to your battery. Cool, so that's...
You can follow up on the battery backwards.
Yeah, you can, exactly, yep, and you could locate it. We could do it on the Prius later for fun if you want, just cause. But, so you know, to work on that DC-DC converter, you don't just start working on this. This has to go through the whole hybrid vehicle shutdown, make it safe, get rid of the high voltage, the gloves, the PPE and all that type of stuff. Because the DC-DC converter is typically either part of or in or next to the main inverter, which this has the really high voltage. That's why there's orange cables. Makes sense? So you got to go about it following service information really carefully. Okay, cool. I think probably we're okay on some of these. You guys pretty good on voltage drop. You know, voltage drop in the charging system's the same as the starter. If you have voltage drop, the starter doesn't get as much power. If you have voltage drop on the charging system, the alternator may make full power, but the full power won't make it to the system. Make sense? It's going to be dropping voltage on the connections, voltage that the battery should be getting, voltage that the system should be getting. Cool, and if you want to measure voltage drop, here's a good one to show you. So let's just say we got our positive cable, our positive lead on our positive cable. We're going to go ahead and put it on volts, and then our other end of that cable is more at the positive battery. So you guys remember that diagram we showed? You put your positive on the big terminal of the alternator, and then you put your negative, the black lead, on that battery terminal, and then you'd actually start it and run it and see how many volts is dropping. Make sense? How many volts is that one dropping?
0.1.
Yeah, 0.1, basically 0.105, but 0.1, that would be a pass for that cable, right? What do we not want?
0. 0.
0 would be great.
Higher than 1?
One would be too much. You could have a 0.2. We don't really want more than a 0.2. We definitely start to run into some problems when it's higher than a 0.5.
So can you?
It's a voltage drop. So like if this is making, let's say it had a 2 volt drop. Okay, let's say this alternator is making 14 volts, but it dropped 2 volts on this cable. What's making it to the system? And so that's not really keeping the battery charged, is it? See how high voltage drop could cause problems in the system. Now a 0.1, good. A 0.2, okay. 0.3 is kind of like technically it fails, but like, you know, maybe we let it go. Once it's over 0.5, it's really like, hey, it fails and we're not going to let this go at all. Mason, go ahead.
Can you get something before the point ever when you're testing it for like a drop or?
Sure. Yeah. So let's just say you had a 3 right here. If it's dropping 3.1, you're dropping 3 volts. If that alternator's putting out 14, the battery's only getting 11. That thing is really, that's going to be premature battery failure over and over. That battery's going to be getting really messed up, right? And so that's kind of what it's showing. And this one is the ground, kind of how we showed the ground, right? We have the 1 terminal on the case of the alternator and 1 terminal on the negative terminal of the battery. We can see how much is dropping on the ground. We're really good there. 0.02 is great for the ground. P.S. Why do you guys think the ground is dropping so little? Think of how the ground makes it back to the battery. It's a big case bolted to a big block, bolted to a big old ground strap with another ground strap and another ground strap. We shouldn't have a lot of voltage drop on the ground because we have really big conductors because it's the whole chassis. Whereas if it's the positive side, it's just the wire. And the wire is plenty large, but voltage drop is going to occur on a smaller wire. And even though the battery terminal is pretty big, it's nowhere near as big as these big engine blocks and stuff bolted together. So we should always have very minimal on the ground. Okay. And then we do this charging system output test. You guys got to remember, this is more than just the voltage test. This starts to calculate, you know, how many loads are on, what's the maximum output, and et cetera. So if we were to initially go to test the alternator, you know, we just want to see, is it making more voltage than battery voltage? That's the first step. Make sense? And if it's not, it already failed. But if it's making 14 volts or 13.5 or 13.6, we're like, I think this alternator is okay, but you don't really know how much it can output. Make sense? So when we get into the regulated voltage, is the voltage at which the regulator is allowing the alternator to create only a small charge due to the battery being relatively charged. So it's only going to put out as many volts as the computer wants because we don't want to overcharge the battery, right? So it's basically like, remember how we want to test somebody's heart condition? What would we do if we really want to know if their heart's good or bad? Put them on the treadmill. If you want to test it like this with just the voltage, that's like telling them walk slowly. And you're like, yeah, everything looks good. You really want to see if their heart's any good? Get them on that treadmill. Same with the alternator. So when we start talking about that, that's when we're going to get into more like using the amp clamp. See this amp clamp right here? We put an amp clamp on here. And then, you know, if we at first were to do no load, maybe it would have 10 amps. Then if we were to turn on headlights and high beams and wipers and stuff, maybe it would make 30. But if you really want to test it, you need one of these old school bad boys. We're going to actually hook up this load tester. You'll actually hook it up to the battery and you can put a load on it. You can say like draw 80 amps if you want it. But like in this case, we're going to rev it at 1500 in this test. Without a load, maybe 15 to 20 amps. Cool. And then as we get a little bit further down into there, we could put some amps to it. So like we're actually going to load test this battery, and you can see just how many amps it'll make, which I think is usually, well, I thought I put it on there, but I'm not. So let's say we put this load tester on there and you start actually load testing the battery. The amps of the alternator should go up. They should be able to make whatever the rated amount is. So like in this case, this alternator is putting out this number. That's like about 82 amps. 82 amps at 12 volts, that would be like, that's an alternator that's working pretty hard. What if the alternator was supposed to be able to put out 90, but it only put out 60? Then it would be like, no, that alternator's no good. Now here's the problem though, okay? Because this is a great tester, but you know what? It's old school, and it's kind of the same as, remember when we talked about battery tests? You can load test the battery, and it's like a guarantee, like it's a really good test. But this is the problem. It's all really similar to taking that medical patient and being like, get up on that treadmill and run as fast as you can, as long as you can. Occasionally, you know what happens, right? Yeah, exactly. So if you want to load test a battery, it's an amazing test. It might kill the battery. If you want to load test an alternator, it's an amazing test, but you might hurt the alternator, you might hurt the battery, this is an extreme test. But I want you guys to at least understand it. You could load this battery to test the absolute maximum number of amps the alternator will put out. But just remember, you might end up with a patient that came in working, and you're like, oh, I tested your car so good, you can't leave with it until you fix it. You know what I'm saying? So this is, in theory, this is a good one. However, this is not real commonplace for us to do. Make sense? Yes, put the amp clamp on there. Yes, maybe put 10 amp load, 20 amp, 30 amp load or whatever. Make sure the alternator can follow. I'm not sure if I'd test it to full 100%. But at least now you know that's how you'd really, really test it. And then how are you going to test for diode ripple? Well, typically you're going to get it up 1,500, 2,000 RPMs. You can set your meter to AC, connect your meter across the positive and negative battery terminal, and then turn on a whole bunch of loads, and then see if you have any AC voltage more than about a half a volt. That would tell you that you have a bad diode if you have more AC voltage than a half a volt of AC. Okay, makes sense? And if it has more, the diode would have failed. If it has a lot more, you might even have more than one diode that's failed. What's the fix for a bad diode? Replace the whole thing. The diode's living here. You're unlikely to get a new diode. The diode would become part of the bridge, and you would try to be like, hey, let me have a rectifier bridge. And they'd be like, a what? A what now? Okay, then we get into the belt. Here, for example, this is an old school V belt. These belts, these belts ride in a single V, and as they wear lower and lower into there, so you can inspect the belt for wear, you can inspect the pulley, you can inspect the belt tension. Too loose would mean what on this pulley? If it's too loose, what's going to happen? It's going to slip, which means it's not going to spin as fast, which means what's it going to produce? Not enough. It depends on how bad it slips. If it completely slips, it'll produce 0. If it slips a little bit, it might just not produce maximum, especially under heavy loads. Make sense? A lot of times if they're slipping though, how would you know that? Squeaking, squealing, and noises. Yeah, exactly. So if you got a car that's squealing and it has a battery light on, you better look real closely at the belt, whether a V belt or a serpentine. Sometimes they call a poly V or a micro V belt. This one, for example, is pretty cut. Yeah. Right, and so the inspection of these is similar. Actually, some of these new ones, they don't really wear. They may or may not crack, or they don't really crack, but they will wear. They have a little orange tool from Gates you can lay in there to see if the V is deep enough in the micro V. But generally, we're looking at them, and we could go crazy on belts, but we won't check to see if the belt's worn or damaged. Okay, and that's kind of just what this is saying. Especially the EPDM rubber don't really crack. They start to wear. This one's cracked, would you agree? That's a super cracked up belt. This may or may not cause a charging system issue, but this is some maintenance that could cause it. But if it doesn't exactly match the symptom, just make sure that we take care of this. This one does, for sure, yeah. But if we test the alternator and this belt is enough to turn the pulley, but the alternator doesn't produce, these cracks may not be causing that alternator to not produce. But I'd say, yeah, you better change that as part of the job. And then what about a belt tension? Have you ever seen one? You can use this belt tension gauge to push on it. It'll move a little needle, and it'll tell you if the belt is too loose or too tight. This is actually a pretty useful tool, but most people don't have it, including me. If it was a belt where I set the tension, I can a lot of times feel it like this, but then what I'll do towards the end is kind of start to twist it and I have a feel that I've developed for how tight I like the belt to be. But when you're new, you don't have the feel yet, so this is a great tool. Now the good news is, on the new stuff, it's a spring-loaded belt tensioner, so you don't have to measure it. The tensioner sets the belt's tension based on its spring. Here's a trick that most people don't know. You see this mark right here? See how those two are lined up? That's a good belt. As the belt wears, the belt starts to get more loose and it starts to get, the grooves get deeper, so it sits deeper and deeper in the pulley, which makes it more loose. It'll start to pull over here. Yeah, it's pulling in. It'll start to pull over here, so how far this is off of this line tells you how worn it is. It'll go worse, 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 worse. Sometimes if I can see that tensioner will tell me if that belt's worn or not. Right there. So some of them even have little marks on them.
Sometimes if your belt's loose, it can skip timing too.
Okay, on these, this belt drives an alternator. That's different than the timing belt. If it's a vehicle with a timing belt, the timing belt's inside the engine and it connects the crankshaft and the camshafts. Those can skip timing for sure, but the alternator is always driven by the drive belt, never by the timing belt, though the water pump might be driven by that timing belt. That's happened a few times for sure. So that'd be a big issue. Okay, and now talking about undercharge, overcharge. If your alternator is constantly undercharging, remember, your battery may not be fully charged. If you have less than half charged battery, that battery is going to fail and fail again and fail again and fail again. Now, when you go to into AutoZone, you're like, hey, this battery you sold me a year ago is bad. I need a replacement. Yeah, I heard. I did. AutoZone. I said AutoZone. If you go in there and you're like, hey, I want a warranty battery. This one's only a year old. And they'll be like, oh, yeah, we'll warranty that for you. Have you checked your alternator? We think you might have a bad alternator. That might be true. Do you see why? If your charging system's undercharging, that battery's under half charge. It's going to fail prematurely. You're going to get another one from AutoZone. They're going to give you another one. That one's going to fail prematurely. Then they'll be like, look, we're going to offer you a free battery starting and charging system test because they're tired of warrantying your stuff. Makes sense? So an undercharging will cause battery failures. That's the main part. And also, another interesting point is if you have a battery that's like really sulfated, your alternator will, how the alternator charges the battery, right? But then when your battery starts to come up in charge, it'll back the alternator off. Well, if your battery is really sulfated, your alternator is going to try to charge it and charge it and charge it and charge it, but your battery is never really going to take the charge. It's never really going to back it off. Some may even argue that a bad battery can cause a failed alternator. So I'd like to elaborate my thoughts on it. While I agree if your battery's bad, your alternator is going to have to work harder, I would say over the long term, yes, it will probably take away life from the alternator. I don't, however, think that if you have a bad alternator, it means you have a bad battery. Or if your alternator fails, it's because of the bad battery. Alternators fail with or without bad batteries. So I'd kind of take it loosely like, hey, my alternator failed. It makes sense that I should make sure my battery's good. Makes sense? But it doesn't really mean that your alternator definitely caused the failure. Cool? So let's say you get into a car with an alternator or charging problem. Generally, we look at all three systems: the battery, the starter, and the charging system. And we like to test all of them because sometimes they can have a bit of an effect on one another. So for example, if your battery is kind of weak, it makes your alternator have to work a little harder. But if your alternator is a little weak, it never fully charges your battery and it can make your battery not last as long. And if your starter has something wrong with it, it can cause too many amps to be drawn out of the battery, which can be harder on your battery, right? So they do kind of go together. But what I don't want you all to be like is, well, if it's got a bad alternator, you should also change the battery too and the starter. And it's sort of like, no, just know there is a relationship there, but it doesn't mean that every car gets a battery, a starter, and an alternator anytime one of the three fail, okay? Doesn't mean that. Cool? Okay, and then this talks a lot about the different specs. So again, how many volts? I don't know. I give you some approximates. How would you know the exact voltage that the alternator should charge at? Manufacturer spec, look it up exactly. Some old cars were higher, some new cars are lower. Sometimes it may give you a really wide spec, like that Toyota spec, 13.2 to 14.9, I think. That's like a huge range. You know why? That's because the computer can have it charge as low as 13, what did it say, 13 volts? and as high as 14.9 depending on the status, right? So we can have these large ranges. All the numbers I gave you were approximate. In reality, if you want the real numbers, you have to look it up for that particular car. Okay, makes sense? You don't want it overcharged. You don't want it undercharged. If it's overcharged, a lot of times it's inside the alternator. An undercharged condition could have a lot more causes, right? So if it's overcharging, we're pretty much looking at the alternator. Make sense? The alternator should not overcharge. That's its job. But if it's undercharging, the alternator may be charging correctly, but it may have voltage drop, loose drive belt, an issue with the wiring, an issue with the regulator, which is inside of it, worn brushes, etc. Makes sense? So this one's easy, and this one has a few more possibilities. That's why we need to start voltage drop testing cables and whatnot. The undercharge is the more common condition. Okay, makes sense? And then again, if we find the issues in the alternator, you know what we're going to do? Replace the alternator. Also, don't forget to disconnect the negative terminal when you start. And the reason that's critical is your big battery terminal right here. If you go to take the nut off of this to get the big battery cable out, and your ratchet goes from this positive to the frame right here, that's a total short. You just blew that fuse that I was making fun of the collision class that blew the fuse because jumping it backwards, you done it now. So you could weld your wrench to the thing too. It's happened. Oh yeah. Cool. And then again, don't just simply, if it has a charging system fault, don't just simply stab the alternator in there. You at least need to do some diagnosis. You should really do the diagnosis all the way as far down to the pulse width modulation signal out of the computer. But if you're not well equipped and you're trying to save money and you were to skip that, you know, I could at least say you'll probably be right if you do your visuals and you check those things, the fuses and the cables and the belt and whatnot. At least minimize your chance of being wrong before you pull out the parts cannon. Okay, there's disconnecting your negative, not a big deal. Cool. There's the belt. You guys are all going to get to do a belt today. Loosen the belt, make a mark on the routing diagram, how it goes. Disconnect the negative terminal, the first step. Pull, this is that big positive terminal. You might have to pull the boot back to get at the nut, right? So some people, what I've seen, they'll leave the battery connected, they'll pull this off and they'll just slide the boot over it. And I understand that concept works, but if you slide the boot over it, this can still touch here. And if this touches here, that fuse is blown, sparks and welding and all sorts of potential. So if I'm doing an alternator, I'm not even gonna shortcut the battery. I'm disconnecting the battery. If I'm doing an oil change, I'm not disconnecting the battery. If I'm replacing a sensor, I'm not disconnecting the battery unless maybe it's related to an airbag, in which case I may or may not. And today, I would skip it. But if I'm doing an alternator or a starter, the battery's getting disconnected because these big ones, that's messed some stuff up right there. And then a couple of tips and tricks. When you go to pull the alternator out, it's really tight. And the reason why is these tend to have like a little bushing in here. So the bracket on your car can vary depending on the machining sizes. These alternators are made to fit the bracket with the variations. So this little bushing right here can slide. When you tighten it up, it slides in, it gets tight. So when you go to pull this off, you ever try to pull it off, it's tight. You might have to work it up and down and wiggle it or whatever, get it out. When you go to put it back in, what I would do, I would try to push this bushing out. It's the nut and the bushing. I try to push it out. You got a couple ways to do it. One, you can bite it and pull it. It'll probably break your teeth. The thing that I would do, I'd actually take the bolt I removed and I'd thread it through here and thread it into there and just hit the end of the bolt a couple times, pow, pow. That'll drive through, drive this bushing out a bit, and then it'll pop right back on.
Don't they have tools to take bushings out?
I'm sure they have tons of tools, but I got the bolt and I definitely got the hammer. Yeah. All right. And just a couple, it's not a lot. It's not a lot, just a little bit. The other thing you could do is you could vice grip it and kind of wiggle it around. You could put it in the vice right here and just wiggle. All that helps. The thing I've seen new people do, if they pull alternator and they go to put it back on, they'll just fight it. They'll just fight it and be like, it won't go, it won't go. They'll just fight it. It's probably because of this. That happens all the time. All right. So it's not really rocket science. Sometimes getting at it's a little tough. Cool. Putting it back on. Here's that bolt that I would have thread in and hit that bushing to back off a little. Connecting the big positive. getting the belt back on, cleaning up the battery terminals, making sure the light's out. Okay? Now that's most of it. There was something I wanted to explain here. We talk a lot about this charging system test, and this should have mostly made sense to you how we load test it, when in reality, probably what we're going to do is those good battery testers, they probably have a charging system test. So if you want to test it a little bit more by the book, a little bit more modernized, the book actually uses this old school machine, and it's good. This is a really good machine, but this is way outdated. If you go to work tomorrow and they say, oh yeah, go do the battery starting charging test, you're going to get a little battery tester. Remember the blue ones we used? A little battery tester, you hook it up, it's going to give you the option, battery test, starter test, charging test. You can do all three of them if you want. So this, while true with the amp clamp, is a really good test, but like typically we're going out and we're just pressing the OK button on the tester, and it's going to tell us, start the engine, turn the lights on, turn the lights off, rev the engine to 2000, right? So in its most simple form, when you actually go to do the diagnosis, you will probably be leaning pretty heavily on some sort of an automated electronic battery starting charging system tester, okay? So I'm good with that, but if it fails the test, that's when you might need to like employ some of these different types of techniques to find out like what's really wrong. Is it the actual alternator? Is it one thing or another thing? These types of things. Okay, makes sense? That's my main takeaway. And then when we get out there, you guys are going to do some basic testing. The first thing I want you to do right off the bat, get a meter, test the battery voltage. Make sense? Then start the car and interpret the new battery voltage, and you tell me whether the charging system is charging or not. Okay, that's your very first assignment. Make sense? Alrighty, you guys, I think we're gonna call it